Thank you. Ilya Sergey is a tenure-track faculty at Yale-NUS College and School of Computing of the National University of Singapore. Before joining NUS in 2018, Ilya was a lecturer at UCL in London. Ilya does research in programming language design and implementation, software verification, program synthesis and repair. So that is the formal introduction. And informally, hello, Ilya. It was lovely when you were in London, and it's nice to see you now from Singapore. At some time, I don't know what time it is.
It's coming, it's coming. The chances are improving. Thank you so much, Philippa, and I wish to start by thanking the organizers, Philippa and Natarjan and the others, for kindly inviting me to speak at this wonderful workshop. I'm so happy to see many people, and I hope it to make worth your while. So today I'm going to talk about one of the latest pieces of the work that we have done in my lab at National University of Singapore, something that I'm very, very excited about. So the work has been done in collaboration with Birkedal, who is a PhD student advised by me, and also Ahmed, who is a cryptographer by training, and now he's the president of Zelica, fintech startup. All right, so we are at the workshop on Vafeiadis, from theory to practice. And so it happened that in the past few years of my career in programming languages, I was mostly focusing on the theory of things such as functional languages and abstract interpretation, and also looking at higher order static analysis. And some of you might know that I've done some work in separation logic and concurrent separation logic. So the reason why I'm so excited about this work is that this set of topics that are very dear to my heart, they all came together to be useful for something really practical. And this is the cause of using them is improving the scalability in modern blockchain protocols. So let me just page back to the title of my talk, which is called Practical Smart Contract Sharding with Static Program Analysis. And the title has both the problem and the technique. So here the problem is sharding of smart contracts. If it doesn't make so much sense, bear with me. I will explain in a couple of seconds. And the technique is something that probably doesn't raise any questions in this particular audience. And this is a static program analysis. So more specifically, what I'm going to talk about is how to improve the throughput and scalability of modern blockchains that support smart contracts. I wish to thank Maurice for giving a very nice introduction to the topic yesterday, so I don't have to do that. And I'm going to do that, show how to do that using static program analysis. So here's the problem. Blockchains don't really scale. So Bitcoin, Ethereum, and other blockchains that you know, unfortunately, their performance and their throughput becomes worse the more people are using them. So here is a blockchain one-on-one, and I'm not really going to go into the details. Essentially, the blockchain protocol gives us a mechanism to reach the consensus within the network of nodes who all together serve the shared purpose. And the purpose is to replicate certain state, which is blockchain state, and also replicate some executable code that governs how the pieces of the state are changed over time. So these pieces of code traditionally referred to as smart contracts, but you can think of them as replicated state machines or even objects in object-oriented programming. There is really not that much difference in this mental models. So here, for example, I have three particular objects. One implements a counter with a single method to modify its state called increment. I also have something that keeps track of tokens. So this is a very popular kind of smart contracts that tells how much of virtual currency different users identified by their addresses own, and they can also transfer that to other users and check their allowance. And finally, the applications are quite diverse. So for example, we can have a smart contract for domain registry. So the way the state of these replicated state machines is changed is by external clients interacting with the protocol by sending transactions to the network of nodes. And the network of nodes takes care of validating those transactions and making sure that they are applied to the contracts and the state is correspondingly replicated. So for example, here we have three transactions, each directed to each particular contract, and you can think of it as of a method invocation. So the reason why the whole thing is called blockchain is the transactions usually are packaged together in the batches called blocks, and the blocks themselves are ordered. Therefore, we can have the entire ledger, the entire log of evolution of our replicated state. And the consensus protocol serves the purpose of keeping this ledger consistent. So the more transactions keep coming, and as you can imagine, they all go to the same network. And the more transactions we have, the more time it will take for the nodes to process them, but also to validate each individual transaction. So the story repeats, and as our blockchains become more popular and some particular contracts in them become more popular, the volume of transaction grows. And this is where we hit the main scalability bottleneck. So unfortunately, nodes have limited bandwidth, and also they have limited processing power. So what can we do about that? Well, since many of us are working in the areas of concurrency parallelism, the natural thing is to split the workload between the nodes and make the processing of transactions go in parallel. How can we do that? Well, instead of one monolithic network of nodes that all need to agree with each other, let's have multiple subnetworks. And let's split our replicated state that each subset of our network called shard will take care of certain contracts. And as long as these contracts do not interact with each other, and there is no any overlap in the transactions that affect them, this model works really, really well. And this is what sharding does. And obviously, as 90% of ideas in system engineering, this is an idea that has been pioneered in database community. So that's why it might sound very familiar. Well, okay, and at this point, it works kind of well, because now these three shards, they can just each take care of processing transactions that are relevant to the piece of replicated state that they govern. And they can also communicate with each other by means of broadcast, bringing the other shards up to date with the state that does not belong to them. Unfortunately, sharding, as I have presented now, also has quite a number of limitations. And these limitations become particularly obvious when we talk about parallelizing interactions with smart contracts. So consider, again, the same picture. Things work nicely if each shard has certain contracts and all the transactions go this way. Unfortunately, some contracts are much more popular than others. So you probably all read articles about how an individual contract is being so popular for a fairly long period of time that it causes the congestion of the entire Ethereum system. So typically, the situation we see is something like that. All transactions, they still go to the same contract, so this particular shard will become a bottleneck. Okay, so obviously we want to parallelize our shared contract executions. And here's the intuition. If we can split a state of a blockchain, which already by itself is a replicated state transition system because there are certain rules according to which this protocol works. So this way we can have sharding and we can have the desired parallelism for simple transactions. So in a way, smart contracts is also something that defines a state transition system. So the only difference is that the code for those smart contracts is quite diverse, because this is not something that is embedded into the protocol. This is something that the users define and deploy by means of replicating this code. And then all the nodes follow this code. So, but the idea is that if we can replicate a particular state transition system, which is blockchain protocol, how about we try to apply the same idea and also extend the sharding idea to the smart contracts? Okay, to put more generally, the question is, does the code of the contract define a shardable or parallelizable state machine? And this is a question that is better be rephrased in even more general terms. Does the code have a certain property of the interest? And now, since most of you are the experts in verification and programming languages, you can recognize that this is a question that we typically answer by some sort of program analysis. And the good news is that indeed we can shard contracts the same way we shard blockchains. And in order to uncover these opportunities, we need to build a technique, which in our case is going to be based on the variable studied apparatus of abstract interpretation and static analysis. So to jump directly to the contribution of this work, we identified a number of mechanisms for parallelizing Ethereum-style smart contracts. And we have developed a static analysis, which we call co-split, that infers the strategies to execute smart contracts in parallel. The smart contracts have to be written in a particular programming language. So this is a language that is not Turing complete, and it's a functional, strongly typed ML style language with no journal recursion. So actually it has many nice properties, and this is why it's so pleasant to build static analysis for it. But we went further and we picked a production level blockchain which we made to support this language natively. And we have integrated this static analysis into the process of creating and validating transactions. And after that, luckily, this blockchain had a number of non-trivial, several dozens of non-trivial contracts. So we could evaluate the inferred sharding strategies in practice. And we noticed almost linear throughput increase as the number of shards goes up. So the more you split your network, the better your parallelism becomes. And this is exactly what we want. So more threads, more parallelism. Well, if only it worked like this in the real life. Okay, so this is the language. I'm not going to spend too much time on it. So we have a paper that took a couple of years back. You can notice that this is a language that has a syntax which probably is pleasing to most of you. It has lambdas, it has let expressions, pattern matching, and it also has type functions. So you can think of it as an explicitly typed system app. So there is no elaboration. It's a very, very simple language with everything being explicit. So smart contracts written in it, they usually look like that. So there is an imperative fragment and there is a functional fragment. And all interactions with smart contracts, they are structured as transitions. So smart contracts in Stella are quite literally state transition systems. Okay, and what we are going to do is we are going to develop static analysis to infer opportunities for parallelism based on two simple ideas. So the first idea, there was a good reason why I mentioned the fact that I did some work on the separation logic or concurrent separation logic. So as Derek Dreyer likes to put it, separation logic is probably should be called the ownership logic because it's about who owns what. And here we already had this idea of ownership represented at the level of individual contracts. So if we make each shard own a particular contract and only work with it, then there is no way the other transactions can interfere with it. So we are going to take this idea slightly further and notice that even individual contracts, such as our fungible token, or in this case, crowdfunding, have a very natural way to split them according to, let me put it this way, fractional ownership of this estate. For example, if your contract is something that implements a crowdfunding campaign, then you can effectively donate to this contract in parallel. And different shards do not have to own the whole contract. They only need to own a part of the estate. And this way, the transactions come into this contract will not affect each other, so they can be really processed in any order, thus enabling parallelism. So why exactly this parallelism is safe? Well, because if we have the disjoint ownership, that means that concurrent interactions, they commute. And this is where the second idea comes. So how about we generalize the idea of ownership to the to arbitrary commutative effects? For example, this is a very simple Scala contract that only does one implementation, and something that should have probably written in one line, it does in four, but it increments a shared field by one. So obviously, this transition happens atomically, and it's very easy to notice that this transition can be invoked multiple times in parallel, and as long as it's atomic, all these interactions will commute. So the second idea is we can actually try to infer which interactions with the contract they commute. And they do not have to have disjoint state footprints, so to say. So the only thing they need to do is to work in a state in a way that commutes with other similar interactions. So this is a picture that shows a standard mechanism in how ordinary money transferring transactions are sharded. Here we have four accounts, A, B, C, D. So A transfers money to B and C. And as you can see, these two transactions, 1 and 2, which both originated A, they are really not commutative, given that A might not have enough money. So if A doesn't have 30 units to make transfers to both B and C, then the outcome will be different based on which transaction landed first, for transaction 1 and transaction 2. However, C gets 2 transfers, both are incoming, and these 2 transfers come from AD. And these transfers, they are commutative because they both only increase the amount of currency that the C has. And this is the way the sharded blockchains work. So at the level of money transfers, it's very easy to argue that transfers that only add to the balance they commute, and this is something that we can do very efficiently in parallel. So we are going to do the same thing with the smart contracts with one caveat. So unfortunately, it's not that easy to infer this commutativity information. For example, we have 2 operations here, increment and double. And well, double commutes with itself, and increment commutes with itself, but they don't commute with each other. So unfortunately, the effects, they do not compose in a way that gives us the same state. And
Ilya, can I just say you've got 5 minutes?
Wonderful. I think that's more than enough. Thank you, Philip. All right, so the idea is that we are designing the analysis using some ideas from surprisingly Glasgow Haskell compiler in a way that determines how many times a contract uses a certain piece of state. And if it uses only once in combination with some constants, we can assure that this operation actually does commute with itself. Otherwise, like in our double, it doesn't. Okay, I really am not going to go deep into the details. I'm just going to say, well, now this information about operations that use certain pieces of state just once and do certain operation can be effectively captured as an effect analysis by means of abstract interpretation. And the only interesting bit in it, which quite surprisingly comes from Glasgow Haskell compiler, is tracking the cardinality of how many times certain variables are used. Okay, but the analysis is just the beginning. So what happens after that, once we collect all this information about reads and writes into certain pieces of state, we start transforming them into something that we call Sharding signatures. So Sharding signatures is something that tells what exactly should be constraints on the particular transaction in a way that it can be executed in parallel, or it needed to be scheduled to be executed sequentially. So the analysis results are turned into these Sharding signatures. And the Sharding signatures say things like this. For example, based on the fact that this component of the contract is being both used as in condition and it's also used to be modified, the shard that manages this contract really needs to own this piece of state. However, this piece of state is used in an additive way. So the contract doesn't have to know it because all the changes performed in parallel in the similar way, they will compute. So the only interesting component here is that we need to introduce something very similar to the notion of weak reads in weak memory models like TSO, because once we start working with the contract in parallel, we should accept that for certain periods of time, some shards might see a stale value, which usually is not a problem, but this is not exactly something that is advertised in a blockchain system, which usually have very strong consistency. All right, so the way it works is that the user, when she writes her contract, she decides how and which transitions of she is going to shard. She runs the analysis, and providing the set of transitions that she wants to execute in parallel, our tool produces a series of constraints. And well, obviously, if we want to have more transitions running in parallel, the constraints are going to be more restrictive. So it's actually the only design part that we didn't manage to fully automate and still require the user input. So typically, it's wise to pick 2 or 3 transitions that work well in parallel, but we provide some support to estimate what's better for sharding. So the last bit, a couple of minutes on how exactly that has been integrated into a real world system. So this is a big scary picture of a distributed system, which in fact only has 3 important components to focus on. So when the transactions come, they're being dispatched, and they either go to one of the shards that work in parallel, or they go what's called this directory service committee, which accounts for executions that need to be done sequentially. So it's parallel versus sequential. So, and these lookup nodes are the nodes that take these signatures into the account and decide whether certain transactions satisfy the constraints. So it can go to one of the shards, or it certainly needs to be processed sequentially. So we integrated this analysis of ours with the public blockchain called Zilliqa that supports Stilla. The way it works, that the designer of the contract runs the analysis, stores the sharding signature along with the contract, and when the new transactions affecting this contract come, they are being dispatched according to the signature, and also the results are being merged according to the merge strategy. So turns out that the analysis is actually pretty fast. It works certainly not slower than the type checker, and it's probably linear in the size of the program, so it doesn't open any avenues for denial of service attacks. And as the number of shards increases, so does the throughput of the system. So when you can see the number of transactions per second actually grows with the number of shards, with the exceptions of 2 particularly interesting contracts which require too much of footprint ownership. So it's very difficult to put the transactions to the right shard to fully take advantage of the parallelism. But on the other hand, there is no performance degradation. All right, so there is a number of limitations, which I'll be happy to discuss if there are any questions about that. One interesting piece of future work is actually sometimes our analysis fails to identify the sharding opportunities, in which case we have to rewrite the contracts. But this rewriting is pretty much mechanical. So I have many colleagues who are interested in the program repair, and this is something that we are currently looking at. So how can we help the developers to write the contracts in a way that will be more parallelizable than they are? So to take away, I have introduced probably, okay, maybe not introduced, but I brought up this idea of sharding, which is a solution to the scalability problem in blockchain consensus protocols. And we have observed that blockchains with smart contracts allow for quite a lot of parallelization in a pessimistic way. So by inferring certain signatures, we design static analysis that relies on the ideas from separation logic and the Glasgow Haskell compiler and infers state ownership and operation commutativity. We integrated this technique into real-world open source blockchain and observed non-trivial increase in the transaction throughput. And there are more details which are all available in our upcoming PODI paper on this scope. And this is all I have. Thank you so much.
Thank you very much, Ilya. And I noticed there's a couple of questions in chat. Thank you. I'm going to invite the people to ask the questions themselves. But just to say, if anyone doesn't want to talk, feel free to put it in chat and I will ask the questions. But Adam, would you like to say your question?
Sure, and it looks like my question may overlap Phil's question significantly. Basically, in sharding schemes, we usually expect it pays off because most operations can be routed to and run on single shards. But we also expect there are occasional more expensive operations that have to go across shards. And I didn't see any explanation here of how that works. Is it because the smart contract domain is different enough from normal database workloads that we don't need to have cross-shard operations, or there just wasn't time to tell us about that, or what?
Wonderful. Okay, thank you so much, Adam, for clarifying that. This is a fairly common concern. And to rephrase it, what do we do with transactions that inevitably affect the state of multiple shards? Well, in this case, let me just switch to the picture that I had for this particular scenario. We have a fallback strategy, which says that there is a dedicated shard in which such transactions need to be handled. So in fact, the signatures that we capture, they provide enough information to know whether this transaction is going to cause something that otherwise would be cross-shard communication. And these transactions are very conservatively sharded to, routed to the piece of network that takes care of that. So one confusion that I might have caused is that there is no state sharding here. So everyone has the same state, which is being reconciled between the epochs, which are fairly short. So essentially, the parallel processing happens in epochs, and between the epochs, the shards talk to each other by means of broadcasts, and they all are getting the same state, after which the new epoch starts. So that's why accessing the state in the different shard is not really a problem that we have here.
So the important thing is that the summary of one epoch is a lot smaller and more efficient to process than the complete transaction flow. Otherwise, you'd gain nothing, right?
Absolutely correct. Yes. So this was obviously the very practical question that we evaluated. So to merge the results of the transactions is much faster than actually execute them from scratch.
Okay. So that at the end of an epoch, you basically run a protocol that gets everyone to agree on the state.
Yes. So we run the merge operation, which is contract specific in these cases.
Got it. Thanks.
Thank you. Thank you, Adam.
Phil, would you like to say more?
Sure. So you said we should say hi to people we don't often say hi to. So
hi, Philip.
Hello, especially to Ilya. So I'm going to put, I think my question is basically the same as Adam's. I didn't quite follow your answer to Adam, because you said, well, some transactions that are not commutative go in this special shard, but I don't see how you can necessarily separate those from the ones that are commutative. But let me put that in a very simple form. Much as you and I like smart contracts, let's consider just the stupid case of transactions, because that's also an important one to shard. So it's obvious to me what happens if you've got A and B that are exchanging money with each other. You can put them in one shard. C and D exchange money with each other. You can put them in another shard. But alas, we don't have partitions like that in the world, right? We can't tell in advance which cliques are only going to exchange money with each other and not with other people. So can you give me an intuitive explanation of what you do for the general case of transactions?
Yes. So if by general case of transaction, you mean the transfer of funds from one account to another, as I have on this slide, is that what you mean? Yes. So the general sharding strategy is based on the disjoint partitioning of the set of addresses of the parties. So all transactions that are emitted by A is going to be processed in a single shard. And these shards will take care of sequentially ordering these transactions to avoid any anomalies, in particular the double spent by A. However, all the transactions that in this particular picture, for example, the transactions that are emitted by A and emitted by D, they don't have to be processed in a single shard because A and D, they have different addresses. And in fact, this is not a problem because in this picture, the transactions which both increase C's account, they can be indeed processed by different shards. And then the state is going to be reconciled using a form of three-way merge to bring up C's balance up by 35 units.
So which shard does C live in?
It doesn't really matter. So it might live with the same shard as A or D or some third shard. So
Okay,
the point is that—
fine. I'm sorry I'm being so stupid, but let me just try to get clear on how this works. So A and C say live in one shard. That's fine. Now D wants to pay some money to C. So that requires some bit to happen in D's shard where D loses the money and some bit to happen in C's shard where C gains the money. So how does that work?
I think the answer might have been that he shuts down concurrency after running a simple analysis to check for hardness of the next few transactions. Is that right, Ilya?
I think that might be an answer to a different question. In this case, what happens is that the parallelism ends between the epochs. So in the parallel execution, A transferred to C, D transferred to C. Those two different transactions got processed by two different shards. But at the end of the epoch, the shards are going to communicate with each other by means of broadcast and convey the deltas to each other. So from one shard, we will know that C's balance went up by 20. And from another, we will know that it went up by 50. And by three-way merge, we will know that altogether it went up by 35.
Okay, so there'll be a proxy for C in D's shard, which accumulates the money that's paid to C, and then that's broadcast at the end of the epoch.
All right. So the state is fully replicated, and it's being reconciled by means of merge between the epochs. So like C's state lives in both shards. We only care about the deltas to C state.
I see. Okay. That's very helpful. Thank you.
You're most welcome. Thank you for the great question.
Okay, I think I should leave it there in the interest of time. I'd like to thank Ilya very much, and please, stop sharing. But also thank you very much, Phil and Adam. I mean, actually, that's one of the better discussions I've seen on Zoom. That was really rather good. So more please from the other participants. I'd now like to say hello to Lars, and would you please, share your screen, and we will start the session.
Yes, can you see the slide now?
Yes, thank you, Lars, that's fine. So Lars is Professor of Computer Science at Aarhus University, where he heads the Logic and Semantics Group and the Center for Basic Research in Program Verification. His main research interests lie in the area of logic and semantics of programming languages and type theories. And that's the formal bit of the introduction. And I'd like just to say, as an extra, I've never worked with Lars before, but during COVID, we've had some of the most delightful discussions together, working together. And I'm really looking forward to hearing your talk, Lars.
Well, thank you very much, Philippa, and also thank you very much for the invitation to the workshop. Very happy to be here. So I'll tell you a bit today about program verification on a capability machine in the presence of untrusted code using our IRIS program logic framework. I'll start by telling you a bit about IRIS. So it's a higher order concurrent separation logic framework implemented and verified in the COG proof assistant. It's also the name of a joint project that we've been developing over the last 6 to 7 years. And the main groups that have been involved is the group here in Aarhus, the Logic and Semantics group, and then Derek Dreyer's Foundations of Programming group at MPI, and my former postdoc Robert Krepper's group at the Radboud University in the Netherlands. Nowadays, there are also several other international groups involved. And there's a homepage here that you can find publications, some tutorial material, and code, etc. that you can download if you're interested. So when IRIS ships, it comes with a base logic that's implemented in COG. And then there's also a programming language whose operational semantics is defined in COG. Then on top of that, there's a program logic, which is defined in the Iris base logic, with which you can then reason and prove programs correct. Since the program logic is defined in the base logic, the program correctness statements that you get will be formulated inside the Iris base logic. So there's also a special adequacy theorem of Iris that's shown relative to the model of Iris, which allows you to sort of extract a program correctness property that only refers to the operational semantics as defined in COG. So I mentioned that Iris is a framework, and what I mean by that is that users can define their own programming language that they're interested in, and then define their own base program logic using the base logic, and use that to get a program correctness notion that they're interested in. In a bit more detail, the base logic of Iris is an intrusionistic higher order logic with connectors from the logic bunched implications, the star and the one, then some modal operators for reasoning about ownership of resources, including ghost state, which can also be used to define notions of invariance and so on. There are also modal operators for guarded recursion, so you can have recursively defined predicates, and there's a loop rule for reasoning about recursion. There's also a modal operator that allows you to recover sort of standard intrusionistic higher order logic without resources. That's this box modality. And the soundness, as I said, is proved using a model construction. And because the resources can also involve predicates, this is also known as sort of higher order ghost state, it's slightly non-trivial to prove this model construction. It involves a solution to a certain kind of guarded recursive domain equation. But that's done once and for all, and then users don't have to worry about that afterwards. And it's a framework, as I said, in the sense that users can define and instantiate it by defining their own operational semantics in COG, and then use the base logic to define a notion of weakest precondition and Hall triples in the base logic for the particular programming language that they're interested in. Typically, if it's for partial correctness, this would be defined using a guarded recursively defined predicate. Then you prove soundness or proof rules for this weakest pre definition and your triples using the base logic. And finally, you prove an adequacy statement expressing that the internal definition of these Hall triples and weakest preconditions entails the desired safety property of your program, which is then a pure statement in COG, not involving Iris. And this uses the adequacy result for the base logic that's based on the actual model construction. Finally, I want to mention that there's a proof mode for Iris that allows you to work with Iris inside COG and do proofs interactively, much in the same way as you construct proofs in COG. So there have been a number of applications of Iris. It was originally developed as a higher order concurrence operation logic for reasoning about partial correctness. And so it was first used to verify fine-grained concurrent data structures, challenging ones with helping and so on. And since then, there have been a number of extensions, for example, to the logic, for example, with prophecies, ways of reasoning about time credits, randomized program, weak memory models, crash safe systems, and even also distributed systems recently. Another line of applications has been to prove semantic type soundness results for expressive type systems. That's the idea where you give an interpretation of the types of your programming language as Iris predicates, and this allows you to combine syntactically well-typed programs with syntactically ill-typed programs that at the end prove correct by hand. So you interpret your types of the programming language, as I said, using predicates in Iris. You can notice this iprop here, and typically you do that as a sort of unary logical relation. And then you can leverage the features of Iris, for example, invariance and guarded recursive predicates, to define this interpretation in a simple way by induction over the type, even if the type system contains challenging features such as references and recursive types. So this has been done for ML-like languages, the dot variant of the dot calculus underlying the Scala type system, variants of calculi for the Rust type system, and even for session types. There have also been relational models developed for reasoning about contextual refinement. So that's following sort of roughly the same outline as above, except that here now you're doing a relational interpretation of your types. And for example, this has been used for reasoning about type and effect systems to prove soundness of a parallelization theorem based on the types and effect. Recently, there have also been relational models developed for reasoning about language-based security properties such as non-interference both termination insensitive and timing sensitive notions for sequential and concurrent languages. And that involves, again, unary and binary logical relations and rotational types. And so today I want to tell you about another application of IRIS, namely what we call series, which is for verifying programs on a capability machine in the presence of untrusted code. So here the idea is that we instantiate IRIS to reason about low-level capability machine programs. And there are no types here, but still we define a kind of untyped or unityped logical relation, and we use that to formalize semantically what capability safety means. And thus, when we want to prove a property for a program that calls some untrusted code, then we can rely on that semantic property specified by the logical relation. This is joint work with a bunch of people I've listed here below from Aarhus University and from KU Leuven and the Free University of Brussels. So what are these capability machines? So a capability is an unforgeable token of authority. You can think of it as a fat pointer with a permission, read only, read, execute, read, write, execute, enter or nothing. And it has a bound of authority from B to E and then a current address A. And the idea is that then the capability machine, when it executes, for example, a load and store instruction, then it dynamically checks that the address is within bounds and that the permission actually permits the action. And if all the conditions are met, then the instruction succeeds and takes place, and otherwise the instruction fails. And these capability machines have been studied for a long time, and they're interesting because they provide a sort of fine-grained privilege separation between different compartments, as in contrast to sort of coarser-grained notions that we know already, like virtual memory and so on. They also provide a low-level form of object capabilities. On the M machine, these are called enter capabilities. In the cherry system, it's in the form of sealed capability pairs. And the good thing about capability machines is they can enforce invariants that we know and love from high-level languages, even when we link with unknown machine code. And there's a lot of experimental systems research and evaluation being done in the Cherry group in Cambridge. And also at present, there's a big project run by ARM called Morello, where they're trying to actually build processors with capabilities. In our work, we focus on developing new semantic techniques for proving properties of capability machines, and also use that to propose new capabilities and applications, for example, more efficient calling conventions that you can then prove are actually safe. So the operational semantics of the capability machine is specified using a kind of standard state transition system approach, where you have registers and memories that you can then transition between. So for example, one transition could look like the one I've shown here, where the PC has this form that it points to some address A, and in the memory, you can find some integer that decodes to some instruction I, and then you can execute the instruction and go over to the new register file and new memory. And there's a bunch of instructions that include some of the standard assembly-like instructions, and then some particular ones for capability machines. I'm not going to go through those today. So let's just consider a small example of how this capability machine can be useful to enforce some high-level properties. So to explain it, I'll first, rather than showing the assembly code, I'll give you a high-level code sketch, sort of written in some ML-like language. So here's a program which first allocates some memory and stores the value 1 in it. Then it restricts the capability that it gets from the allocator to be just read-only. And then it calls some unknown code and passes that capability to it. And then the idea is that afterwards you'll check that the value in location X is still just 1. And then you halt. And then the idea is, right, that if you run this program, then it should continue to be the case that the assert here would not fail. And we model that using a memory location with some flag, and just say we want to keep that to be 0 all the time. That means that the assert hasn't failed. And this will, of course, depend on the fact that you only pass a read-only capability to the unknown code, but also on the local state encapsulation, which is enforced using these enter capabilities that I mentioned earlier on, so that the unknown code can't just access the local state with the X points to in some other way. Now, how can we prove such a specification using the IRIS program logic framework? Well, first we instantiate develop a program logic to formalize the specification and prove sort of the known part of the code that's actually shown on the previous slide. So that corresponds to the custom program logic that I mentioned earlier on. And then we define a logical relation to capture the notion of capability safety so that we can reason about the unknown code. Usually when we do logical relations, and you've seen those for type languages before, the types will guarantee the absence of runtime errors. Here, as I said, there are no types, and it's also okay if the runtime faults, right? If the capability faults, that's okay. The point is that the logical relation will capture the properties that hold if the capability machine does not fault. So in the remainder of the talk, I'll sketch how this is done. And I'm doing this for a sort of simplified setup where we don't have a stack and there's no enforcement of control flow integrity. Those kind of properties you can see also being dealt with in our PubL paper if you're interested. So for the program logic, we have some resources, sort of separation logic style for registers and memory. Now, and then one issue is that since these low-level programs that are stored in memory, need to figure out what should a Hall triple or weakest precondition look like. And we use a format sort of like what I've shown here, right, where you have that the PC will point to some capability and an address A, and in that address A, you'll have some word. That's the word that if you decode it, it will actually be some instruction, and then and that's the instruction that you want to execute, right? And then you want to have a weakest pre, and then some post-condition Q. And so because of the fact that the programs that are stored in memory, we don't really have any expression really to put here in the weakest precondition if we're just going to reuse the existing notion of weakest pre that Iris ships with. So what we do is that we sort of come up with some kind of execution mode. Here I've just written single step, if it's just a single atomic instruction we want to deal with. And then the format looks as what I've shown here. That's the decode from before. That's a valid PC condition, which expresses that the address that the PC points to is within bounds, and that permission is read execute or read write execute, so that you can actually execute the instruction. And then, as I said, this sort of single step here is just to allow us to reuse the existing notion of weakest precondition that Iris ships with. For complete programs, we also have another execution mode called sort of repeat single step here. And the intuitive reading of such a formula here in Iris is that suppose you add some context and you have some Iris invariants around, then this spec that we have here above holds that if under the assumptions P, and you start executing the program stored at the location W, then either the machine will fault, that's the capability check, or diverges or terminates, and all the Iris invariants that you have are preserved along the way of the computation. Right. Then then you can show a number of proof rules for each atomic instruction of the machine, and some structural rules for sequencing and so on. You have some Iris rules for reasoning about invariants, etc. And these are all established and proved in Iris using the definition of WP and the operational semantics. Now, what about the logical relation? As I said, the goal is to reason about unknown code, and we need to define what it means for some unknown code to behave well. And the idea of the capability machine is that it behaves well if it doesn't violate capability safety, whatever that precisely means. So that's what the logical relation will give us a precise definition of. It will define a contract that well-behaved capability machines must follow. And then we'll use that as the interface when we reason about unknown code. So here is actually how the logical relation is defined. So there's an expression relation and a value relation, much like you've seen for other high-level languages. And the idea is that the expression relation says that if the PC points to some W, some word that you are about to want to execute from, and all the other registers hold values that are safe to execute. That's how you can think of the value relation. Then it will be safe to execute the machine, right? So that's what this definition here says. Then the WP here will hold. And all the invariants will hold at every step of execution. Now the value relation, think of that as the value relation holds for some capability W if the capability is safe to share. And if the word W is just an integer, then it's trivially safe to share. So therefore the predicate is just true. And if it's an enter capability, then that means that that's safe to share if the code that it encapsulates is safe to execute. And since that's something you want to be execute at any time, it should not rely on any particular resources, but only on some other invariants. That's why we use this box modality here in front of the E relation. Now, the read and write capabilities, they give read and write access to the addresses in its range. So therefore, those values need to be safe to share. That's what you can see down here in the right case. For the read only or read execute case, the capability can't be used by the unknown code to modify the words in its range. So therefore, you can have a sort of stronger invariant that can be satisfied. For example, so that means that this predicate here inside a box, that's the notion of iris invariant. So this says that A will point to some word W for which the P predicate will hold, and that's okay as long as that is enough to guarantee that you know that the W is also a safe capability. So for example, P of W could be that W is just equal to some number 42, if you want to maintain that invariant. Okay, so you'll notice that this is a recursive definition, right? The predicates E and V, they sort of appear inside the own definition. And the reason this is well defined in Iris is because the recursive calls are guarded by this later operator here. So this is an example of a guarded recursively defined predicate. Okay.
Lars, can I just say it's 5 minutes, and please can people put questions in the chat? Thanks. Right.
Okay, and then we can establish the correspondence, the usual sort of fundamental theorem of the logic of relation, which basically here has a very simple form. It says that if you have some capability that's in the value relation, then it's also in the E relation here. Intuitively, you can read that as saying that as long as some capability is safe to share, or sort of only gives access to safe memory words, then it's also safe to execute, and it will preserve all invariants. And this requires checking, you know, a lot of possible cases of every instruction and semantics of the machine. So let's return now to our example and see how we can use this. So to do that, we need to have the assembly code of our high-level example program that I mentioned before. And I've shown that here. I'm not going to go through it in detail, but you can see that it has some calls to malloc, and that's programmed in the assembly code. There's a call instruction, some way to restore some locals and some insert statement, and so on. Okay. And you need to have some, and these are the underlying statements here are some macros that I find in the assembly code, right? But you can see in particular this thing that you get restrict this capability to the read-only permission before you make the call to the unknown code. That was the point of the high-level example. Now, to reason about this, right, since you're making calls, you have to have some kind of calling convention here. And since we're now dealing with in a setup where, as I said, we're not dealing with a stack, we have a sort of heap-based calling convention in this case here. So it works sort of like, you know, you allocate some heap space to store some activation record, and then you store the local state there, set up some kind of consideration for where to return, and then also a capability to the local state. Then you clear all the registers, and you have an E capability pointing to the activation record to keep that to be local, and then you jump to the call destination. The details here really don't matter so much for the overall statement I just want to get across. So the full statement is then that we would like to specify and prove for this program then has this sort of shape here. There's some invariants for malloc and other functions around, and there's an invariant for the flag that it should stay 0. And then the idea is, right, that you express here that you have your PC points to some address where you have the code. These are the from G1 to Gn, and G1 is the first address of the code that we just had on the previous slide. And then you have the values there. You have all the points to for the registers, and then in red you have the assumptions for the unknown code, namely that the register there points to some word which is then just assumed to be valid in the value relation, right? That's the only assumption on the unknown code. And then you would like to prove that this weakest precondition here follows from these assumptions. Then, if this is the case, right, then by adequacy of the weakest preconditions, if we can prove it, then we will know also that the invariant, in particular the one here for the flag, will continue to hold at any point during the execution. In other words, the assertion will not fail. And the way this works, the key ideas here of the proof is that you use this definition of the value relation for these read-only capabilities, to allocate you an invariant, which lets us successfully verify the code, in particular that the assertion holds, right? So in particular here, that the value there will just stay 1. And then when we want to do something about the unknown code, then we use the fundamental theorem of the logical relation to know so we can safely execute that unknown code. Okay. And here we use the fact that the logical relation is defined inside the array space logic so that we can combine the knowledge from the logical relation with this other part of the proof for the known part of the code. And finally, apply the adequacy theorem to conclude that the lemma we wanted to actually holds when we're done. All right. So finally, remarks is that I want to mention is that this approach here has been developed also for a more sophisticated capability machine, as I said, with a stack-based calling convention. And then one can use this approach here to prove that the calling convention and the capabilities can ensure local state encapsulation and a well-bracketed control flow, what's also sometimes known as control flow integrity. We have some ongoing work at the moment where we're trying to extend this approach to also reason about memory mapped I/O and enforcement of security properties for peripherals that use this memory mapped I/O. We're also studying some new kinds of monotonic capabilities that can lead to sort of improved efficient temporal stack safety. And we're also beginning to look into interrupts. And in collaboration with some people in Cambridge, we're also trying to work towards reasoning about more realistic capability machines, such as the Cherry instruction set architecture. So let me end here by thanking many of the other people who've been involved in this work here. Thank you so much.
Thank you, Lars. So there's one question in chat at the moment. Please put questions in chat or put your hand up. Thank you, somebody else. So first, David. David Neumann, would you like to say your question, or I can say it?
Sure. I'm puzzling though that I see 3 questions in the chat and Adam's came before
lag.
My question was really sort of general, whether you're using ghost state in this work, and if so, how, and is it higher order?
All right. Yes. So we are using a ghost state basically to encode all the invariants of the machine. Right, so we have a, how should I say it? So underlying this is a kind of state transition system model, also used for the properties that are guaranteed by the capability machine. In particular, because there's also a possibility of when you have a possibility of revoking capabilities, and you can capture that using a kind of state transition system, and that's coded up using a ghost state. Yes.
Okay, thanks.
And sorry, yes, I missed you, Adam. Adam, please.
Quite all right. Lars, am I understanding the definition of that script V relation correctly, that once a memory address gets involved in an interesting contract, it may not be reused for another purpose for the whole remaining execution of the program?
May not be reused.
There's an invariant about an address, which seems to mean that address will continue to have the same specification associated with it for the rest of time. So you couldn't deallocate it and reallocate it in a completely different part of your program with a different contract.
Right. So in this particular one, I think that might be the case. Yes, but that's also why I said. In the more elaborate model that I haven't shown here today, right? There is this way of dealing, for example, with stack code, where you're reusing addresses, right? And that's exactly that. As I said, you have sort of a more involved. You have more involved invariants that are just don't just stay put, as it were, right? They have a protocol for those, how they can evolve over time, and that allows you to sort of reuse memory.
Okay, thanks.
Yeah.
So I don't know, Pete, whether you want a question or just maybe putting a comment. I'll ask a question first and just flag up if you wish. So There's a lot of work going on in the UK about capabilities, in particular centered on the ARM work and the Cherry work, with large funding associated with it. And I know, Lars, that you're you very much focus on essence of and theory of, at least at the beginning. You're working with Cambridge. This workshop's called From Theory to Practice. So what would be your main message to the practitioners, given the work you've done?
Well, that's a good question. What we're trying to do in this collaboration, it's with Peter Sewell's group from Cambridge, right? We're trying to see if we can scale up these models to reason about more realistic capability machines, as I said, right, with large instruction set architectures, and there are lots of difficulties with that, right? Because those systems are so big, right, that you really want to have some kind of machine facility. You can't just define the operational semantics and prove all of these proof rules by hand. You want to derive that systematically from some machine model you have initially. And that's what we're trying to do. And that requires a lot of new work for us to be able to do that. And then also to derive from the operational semantics, some of the basic proof rules automatically should also be doable. So that's sort of currently the kind of things we're doing. And then I think if we can succeed with that, I think we can actually verify some of those programming patterns that the more, let's call it more experimental people have been trying to program with, right? And so I think it goes both ways. So they give us some challenges in terms of other things that we could try to verify. And I think the other way around is by analyzing things sort of in the more sort of theoretical setup, we can also come up with new proposals for new capabilities that can make, for example, calling conventions more efficient. So we have come up with some of those in this work that I mentioned here. And I know that some of the other groups in Cambridge are considering whether they can actually implement this efficiently in hardware.
Hmm. And also, just to continue this, so you're using COC, you're using Iris. How much are you able to automate? Are you finding that the underlying framework is working for you, or is it really quite hard?
Right. So most of the stuff we developed first was done without any automation. Yeah. I mean, or very limited automation, and I mean, I think a lot of it was sort of hard work, you could say, right? But then actually a postdoc of mine has started to do some automation that allows you to do a lot of sort of the verification more efficiently by developing basically sort of, symbolic execution kind of ideas, right? That you also have in other static analysis tools, automated reasoning tools. You can also do that, inside COC. Other people have done related things like that as well. But that actually has reduced the proof size quite dramatically. So that is also important in practice, yes.
Thank you very much, Lars. I think we should leave it there. It's now time for the next talk. So thank you, and please unshare your screen.
Yes.
And hello, Amal, if you're there.
Thank you so much.
Hello. Yes, I'm here. Hi. I have two machines. I'm sharing from one and, video on the other. So let's.
Okay, so I will introduce you. So Amal Ahmed is Professor of Computer Science in the Northeastern University. Her research involves using program language semantics and type systems for reasoning about imperative code, security, concurrency, compiler transformations, and provenance. With her particular focus is on how to build verified compilers that ensure safe linking of code compiled from different programming languages. So I mainly know Amal through conferences, but also through her Oregon School lectures on logical relations, which many of us know, and I very much look forward to this talk.
Great. Thank you so much, Philippa. And thank you to you and Shankar and all the organizers for inviting me. It's been really nice to see all these faces that I haven't seen in a year. That's, really lovely. Okay, so what I'm going to be talking about today is verifying soundness of foreign function interfaces. In particular, a framework to make sure that we can, have our type sound languages and also, oh, wow, there's a lag. A huge lag.
I'm finding it okay.
Do you see my?
Oh no, not sharing slide, not your next slide.
Ah, you don't see my next slide.
No.
Well, that's bad. Sharing is paused. Okay, hold on a second. Okay, so
you'll be on the whiteboard by the end.
I know, that'll be terrible. Play. Okay, let's forward. Oh man.
Amal, if I may, it helps to share the entire desktop.
I know what it is. Yeah, I need to bring.
Rather than just the app, yes.
Rather than just the app, don't share just the app. Share the desktop.
Share the entire desktop.
Okay,
then,
sounds good.
It usually works. Yeah.
Okay, cool.
Thank you, Ilya.
I mean, I hope it helps. I'm not sure.
All right, let's try again. Yes. Thank you, Ilya. All right. Okay. So, so what I want to talk about today is how do we ensure that we have type soundness of programming languages, even as they allow us to interoperate with other languages. Now, we're very good at verifying type safety of a single language. We all know how to do that. You can usually do a progress and preservation proof. But all of our, general purpose languages out there, they allow some form of interoperability. And we all know of different frameworks that allow this kind of thing. Almost every single language has a CFFI. And normally, if you want to interoperate with C, you might want to use tools like Swig to generate the wrappers required in order to generate bindings. There's inline C, which allows you to write very nice C in Haskell. There's OCaml C types, again, a very nice way of interoperating between OCaml and C. But then there are other forms of interop as well, beyond the just I want to interoperate with C kind of world. So for instance, Scala compiles to the JVM, and via that mechanism, it basically can interoperate with all sorts of other languages that compile to JVM and get interop with Java as well. Clojure and Kotlin use a similar strategy. They also compile to JVM and provide interoperability with Java. And of course, this is, old news and well established by now that, the .NET set of languages basically allow us to interoperate as well. So for all of these things that I've listed here, and of course there are many, many more, the problem is that we have tooling to allow us to interoperate between languages, but we never really have verified, type soundness of the language that is of these pair of languages that are interoperating. In the case of interoperating with C, of course, you might say, well, if OCaml is type safe, after we interoperate with C, that's a tough proposition because C is so unsafe. But even when you interoperate between two typed languages, right? No, we don't really know how. We don't have a good framework or a good mechanism for proving type soundness. And again, I want to come back to the thing at the top that we are very good at verifying type safety of a single language. Now, the one piece of really great work that's been done in this space is way back in 2007 when Jacob Matthews and Robbie Findler wrote a paper on operational semantics for multi-language programs. And they basically defined this very nice framework for taking two languages and putting them together into a multi-language, one that integrates both of them by giving a systematic way of placing boundaries between the code of the two languages and then defining an operational semantics for the boundaries that essentially does conversions from one language to the other. These are type-directed boundaries. And, this approach has been used a lot. I've used it a lot in my work, but it stays sort of at the source level. These are not how these tools that I have on this slide are built. So what I want to talk about today is a framework for verifying type soundness that matches how FFIs actually are implemented out there. This is about verifying type soundness of FFIs as they're implemented in practice. And this picture is showing you how, my very rough high-level sketch of how they're implemented in practice. You have code in two different languages. It's not interoperating as so much at the source level, but essentially, or whatever wrappers or binders you have, you're basically compiling down to a target, and at the target level, you have you implement interoperability by inserting glue code between the two pieces of target code that you have here. So what does that glue code do? Essentially, it might do convert from one data from the data representation used in one language to the other, or it might try to sort of, massage the difference between different calling conventions that the languages might use. So this, this glue code or this conversion code is the thing that is actually doing all of the work, and it's the thing that we want to make sure is safely doing the conversions. Okay, and I just want to say that this is joint work with my PhD student, Daniel Patterson. So in order to show you the framework, I'm going to do a tiny little case study. This is basically what I can fit into 20 minutes. So we're going to take mini-ML. Basically, it's a polymorphic language with dynamically allocated mutable references. You can see ref and deref and assignment there. And I have this other language, Afi, which is just an affine language. This is, you can think of it as a super simple stand-in for what I hope to be able to do, which is interoperability between ML and Rust. I'll talk about that at the very end. Okay, so this affine language, I have judgments for both of these right here. Just since we're going, this whole talk is about proving type soundness, I want to at least show you the shape of the judgments. Mini-ML, of course, is completely standard, but for Afi, this omega environment is what keeps affine type variables, affine term variables. I want to draw your attention to the little bit of syntax that is weird on this picture. All I'm doing in this case study is I'm allowing foreign calls from one language to the other, and that's what these are. So these are foreign function calls, and our whole task is how the heck are we going to prove type soundness in the presence of these foreign function calls? Okay, I also have to tell you what we're compiling to, because my picture said we're going to compile to a target, and that's where we actually do the interoperation. For this talk, the target is extremely high level. It's just but it is untyped. So, that's how most compilers are built. You're compiling down to some untyped language, and that's where you have to ensure you're converting properly. So I've picked a rather high level, but still untyped target. And the key thing is that this has runtime failure, because I want to be able to catch certain catch errors, whenever a conversion happens whenever something happens that's not safe, I want to be able to fail. So we have failure in this language. Okay, this slide I just put in to just clarify that, this is an affine, Afi is an affine lambda calculus. So we have these affine variables A that live in omega. And of course, whenever we are in an affine language, we want to make sure that affine resources are never used twice. So that means we split omega when we type check E1 and E2. Other than that, this is utterly standard. And gamma is, of course, the environment for unrestricted variables. Okay, so how do we type a foreign function call? So this is the foreign function call from ML to calling a function, an orange function in Afi. All right. So this function has type tau1 lolly tau2. And in order to type check this, basically what we want to do is we say, okay, we're using a function that's a tau1 lolly tau2, and I've just insisted that this is closed code so that I'm not capturing ML, variables in my foreign code. So I want to call a closed function. What I have to make sure is that my E2 is of type tau2. I need to be able to convert it, from this blue tau2 into orange tau2, so that my E2 is actually of type tau1. I said the wrong thing. So I have to be able to convert it from blue tau1 to orange tau1 to pass it to this function. The function will give me back an orange tau2, which I have to be able to convert back to my blue tau2, which is the result of my function call, my foreign function call. So what I've introduced here is this convertibility relation. A foreign function, when someone designs a foreign function interface, basically what we're saying is you have to make a decision about which types from language A are convertible to language B and vice versa. And here I've picked a symmetric convertibility relation that keeps things simple, and it's kind of simple from a programmer's perspective as well. So you have to decide what conversions you're going to allow between what shapes of types, essentially. And that's what this relation will specify. And then just for the sake of completeness, here's my rule in the other direction. This is when we are in Afi making a foreign call to this ML function. okay? Which again, it's just the dual of that, but convertibility required again. Okay, so here's the recipe for proving your FFI sound. First, well, designing and implementing and proving. First, specify these convertibility rules. When are these types from ML and convertible to types from AFI and vice versa? And I'm going to show you rules for our ML-AFI combination later. Then go ahead and implement these target level conversions for each pair of convertible types. So if you have a blue tau that's convertible to an orange tau, then you need to give two conversion functions back and forth, basically. But these conversion functions are the things that are implemented at this target level. They're target level code. They're going to convert target level compiled code between the languages. Now, to prove type soundness, what we're going to do, the main work that we're going to do is we're going to define a logical relation. This logical relation is unusual in that it is indexed by source types. So it is, this is the meaning of ML types, you can think of it that way, and this is the meaning of AFI types. It's indexed by source types, but inhabited by target terms. This is very much in the tradition of realizability models. The only, similar use of a logical relation indexed by source types but inhabited by target terms, not only, but it goes back to a couple of papers in 2007, 2009 by Nick Benton, one with Nicholas Tabarot, one with Uri Zarfati. So they use this to prove the soundness of a source language, but they didn't sort of do what I'm showing you today, which is to sort of extend it to try to prove soundness of interop. Okay, so here's where the interop comes in. Once you've defined your logical relation, you have a meaning of types, right? So you know that these terms E that inhabit the set of blue types in some sense are the ones that behave the way a blue type tau, this blue type tau should. And similarly for this set of terms, they should behave like the orange type tau that they belong to. Now what we're going to do is we're going to prove the conversions that we're writing at the target level. We're going to prove them sound. And soundness of this convertibility relation simply amounts to proving these two things, that if you have a term that behaves like a blue tau and then you convert it or wrap it with your conversion function, remember this is a target piece of code, you're wrapping it with your conversion function in order to convert it to what should be an orange type or what should behave like an orange type. Then C wrapped around that target code will behave like the orange type tau. That's what it means to convert from blue to orange. And part two is just the opposite direction. So that says that if a conversion function is applied to something that behaves like the blue type, then it'll give you back something that properly semantically behaves like the orange type, which is the essence of what we want, right? Soundness. If you have a meaning of types, that's what your types should mean. That's what behaviors, those are the legitimate behaviors in some sense that you're capturing with these sets. And we want to make sure that conversion ensures that you stay within the right behaviors. Of course, this means that you can fail if, so dynamically enforced type safety is fine as well. And I'll get to that later. Okay, so then we prove type soundness, which is a matter of proving the top level, judgment sound in a semantic type soundness sense. So let me give you a very, very quick look at these compilers for ML and AFI. My case study is simple enough that the ML compiler is really, trivial. It's mostly identity. It just erases types because you're going from mini ML to essentially mini ML, but without types. And then the only interesting thing that's happening here is what happens when we do the foreign function call. And there we just do the conversions back and forth, as you would expect. The plus here just means compile. Okay. All right. Now, what about the AFI compiler? This is a little bit more interesting. Basically, what needs to happen is we are going from an affine language where we make sure that affine resources are never used more than once. But we are going to be living in a world where there is no such discipline. There is no way of enforcing that something is used only once. So what we're going to do is use this trick. This is something that Jesse Tov and Ricardo Pacella used in a paper probably back in 2010. It's a similar trick. Basically, we're going to take anything that's supposed to be an affine resource and wrap it in this thunk, which does what? It basically allocates a fresh reference cell and puts false in it, indicating, nope, this thing hasn't been used yet. All right. Now we return this thunk. And when the thunk is called in order to use the affine resource, the first thing we do is we check, has it, is this set to true, which means it's already been used? If so, fail. Otherwise, set it to true and just return the value. Okay. So it's just a wrapper around that makes sure that nothing is ever used more than once. Okay, so what we do is the compiler basically inserts thunks in the right places in order to make sure that affine variables are not, affine values essentially are thunked and therefore protected. And the rest is, this is again just conversion back and forth. Okay, let's talk about convertibility. I'm just going to show you one really interesting case of convertibility, but let's start with a couple of slightly boring cases. So here's the convertibility relation. I want you to think of this as I decide that this orange type and this blue type are convertible between each other, and I implement it by giving these conversions at the target level. Okay, so what types are convertible? Unit is convertible to unit, int is convertible to int, boring cases, easy. Linear pairs are convertible to ML pairs, right? Simple. If the tau 1s are convertible and the tau 2s are convertible, then we can convert the pairs. As you can imagine, the conversions are really trivial. For the base types, we don't do anything. For the pairs, we just push the conversion in, right? Okay.
Sorry, can I say 5 minutes for
yes.
Amal and also questions, please?
Okay, thanks. The interesting case is this one. When we have a function, how can we convert an affine function to an ML function, right? And this is where things get a little tricky. You essentially, if you, or let's say, this goes in both directions. Let's say you want to have an ML function and you want to wrap it and give it an interface and make it act like it's an affine function. That means when your affine function gets an input, that input should be treated in an affine way. But now if you pass it to the ML function, ML might make copies. So that's the thing you have to prevent. And the way we prevent it is by not allowing interrupt between tau1 lolly tau 2 and tau1 arrow tau 2, but rather demanding that on the ML side, you have to have this thunk. And let me explain why we do that. When you have this, when you take your ML function of this type and convert it to the affine function, what you do is the same trick that I showed you before with the thunk that's wrapping things. You basically say that this E is my ML function. What I'm going to do is produce an affine function that will be taking some input X. And what I'm going to do is I'm going to generate a new cell to contain a flag, which says right now it's unused, but whenever you call this thunk, it will give you the value back the first time, but set the flag to true, which means the next time it will fail. So you will only be able to use it once. And that wrapped thing, thunked thing, is the thing that we pass to the ML function. So that's why we need this, thunk argument here. And the other direction, all we need to do is we need to, if we have a thunk, we need to apply it to unit to sort of move along. Okay, let me quickly give you a look at the logical relation that we set up. So it's a step index scripty logical relation. A lot of this is fairly standard. I just want to focus on the part that is different because of this interaction between ML and AFI. So we're just setting it up and saying that, a value behaves like a type tau in the presence in some world W. That's the basic shape. But what is in the world? A step index, a heap typing, just normal like for ML style references. This is fairly standard by now. This A is a mapping. So basically, you can think of it as all of the references that are coming from ML, those locations live inside, and all of those references that we allocated to contain our flags, they live in A. And in A, we don't have their type. We don't just say that this is a reference and it's a Boolean. We actually keep the value of the flag. Like, what is it right now? So that way we know that we are in this present world. And right now, this is a resource that is used or unused. Once a resource has been used, that's my next point. Once a resource has been used, in the future, it better not look unused again. And that basically is what we get from world extension. This world extension, if you go from a current world K psi A to a future world J psi prime A prime, in the future you have fewer steps. This is standard, and the types of all the ML references better remain approximately the same. But here's the interesting part, that if in the past something had already been set to used, i.e. true, then it better still remain used. You can't just, kind of go back in time and say, hey, I want to use it again, right? So that's the one thing that needs to change. Interpretations of ML types, of ints, these are utterly standard, so I'm going to skip this and show you the one thing that is genuinely interesting here. So what is the interpretation of an affine function, of an affine type? Well, a lambda belongs to this type if in some future world W prime, you give me an argument of the right type of tau1. And then what do? Well, the first thing I do is I take my current world, W prime, which is where I'm about to do the application, and I put a new fresh cell into it. I think I forgot to say freshness, but L is a fresh cell. And I put a false flag into it saying value has not been used yet. And then I go ahead and I substitute X with this thunked protected value. That's, again, going to do just the same thing. If the flag is true, we will fail. If the flag is false, we will give the value back. And then finally, the expression relation. When do expressions belong to a type tau? This tau might be blue or orange. It doesn't matter. It's the same semantics. Well, we pick a heap that satisfies the world and we run. And if we get to an irreducible state, then either that E prime is fail, which means that we want to catch errors at runtime. So failure has to be a possibility. Or, you've extended your world somehow. You are in a legitimate heap and you have a value. That part is standard. Okay, so having done all that, you then basically define, the standard logical relation thing. You give meaning to what should this judgment mean, which basically means you find closing terms to close off your blue E or to close off your orange E. The interesting thing about how we close off our orange E, right, because it might have these free variables, free term variables from gamma and free affine variables from omega. Free term variables from gamma, we just need substitutions for them of the right types and we plug them in, we substitute them into E. But for omega, you have to wrap them. Right? You have to allocate a fresh cell for every single affine variable because it's a resource and it must be protected. You must set the cell to false, just like I've been doing throughout the talk. Now you have to do that for all of these affine variables. And then you take that, you take an input that you're going to substitute, you wrap it in this thunk with a flag around it, guarding it basically. And then you substitute that thunk into this expression. Okay, so once you've done all that, it's back to the recipe. We're basically just proving conversion soundness. If you got your logical relation right and your compilers right, that should go through. And proving type soundness using conversion soundness because you'll need it in order to prove the soundness of the foreign function called typing rule. I just want to end with a couple of comments about what this has been showing us, even as we apply it to smallish case studies. So I've shown you I've shown you a rather small case study, a rather simple example, but we believe that the framework is extremely general, and you ought to be able to apply this to all sorts of different language interoperability scenarios where you have two source languages compiling to a target. Even if you have a source language, like I mentioned at the beginning, that Scala compiles to Java, you get interop with JVM, or if you want to interop with the target code, you can think of your second source language as the target. That's a perfectly okay model. It's just that the compiler for that is the identity, right? So the framework should apply to that as well. Now, what we've been doing, or what we've been realizing as we use this is, there are so many different trade-offs even in the design of FFIs. That's what you start to see that, let's start with, do you want your soundness, type soundness, interoperability soundness enforced statically or dynamically? And that's a trade-off. If you do it dynamically, as I've shown it to you in this talk, you obviously are going to pay a performance penalty because you have a lot of checks all over the place. So how can you get rid of them? You can enrich your type system. You don't have to remain restricted to the type system of language A and language B. Perhaps there's something interesting that you can do in terms of enriching, your type system at one or 2 points in order to facilitate interop that is statically type safe. Then you wouldn't have any performance overheads. And this framework allows you to study that and sort of identify what kinds of features you need, within that in order to ensure static soundness. So another way that entirely static enforcement of type soundness may be possible is if you just allow a lot less interop. So if your convertibility relation is really, really restricted and there's very few types that are convertible between languages, because then you get into fewer messes, basically. So for instance, here, if I hadn't allowed conversion between the functions of AFI and mini-ML, then I conjecture that maybe with one more tweak, I could have enforced safety entirely statically. But of course, that's not a great win because I'm giving up interop in order to get static enforcement. And then if the target is typed, of course, you may need fewer checks as well. Here I showed you an untyped target. So all of these are little knobs that you can turn as you design your FFI. Okay, just a little bit on ongoing work. We've been looking at interop between ML and a kind of safe C. The target that we're using is actually inspired by Cherry and capability machines. So that's how we're getting our safe C. And you know, it's essentially, that's all I want to say. Some interesting things have come up, like, is it okay for us to pass a reference to a Boolean to C as a pointer to a Boolean? Well, what's the problem with that? If you pass it, then C can obviously go and clobber that bit of memory. And suppose that your ML representation of a Boolean was either 0 or 1. 0 is false and 1 is true, and everything else means garbage. But now you've compiled down to an int 64, right? So now you gave it to C. Suppose C puts a 3 there. 3 has no meaning. So C puts a 3 there and gives it back to ML, and now ML is like, I thought this was a Boolean, but it has no meaning. So that's a trivial little example, but basically, if you instead chose to represent Booleans as 0 is false and you know, everything else is true, then you don't have this problem, because no matter what C puts into that slot, into that cell, it'll have a meaning for you as a Boolean. So these are little things of data representation that, you know, you start to see very clearly as you do this. A bit more about view shifting and using C to cast our data to different views is also an interesting bit that's come up. And in the future, I'll just end with this. What we really are building up towards is wanting to design an FFI between ML and Rust and prove it safe, compile that to WebAssembly. But that's future work at this point. Rust is rather complicated. So I'll stop there. Ooh, I've eaten up most of my time.
Thank you, Amal. And we have the Adam Phil double act. So why not Adam first?
Amal, you have some top-level meta theorem here, presumably type safety. If you used a naive system instead underneath that just made every conversion between languages fail, would your meta theorem still hold?
Yes, because everything failed. And this is something I've been thinking about. So I think what you want to be able to do is, in all of the places where you want to be able to give precise errors. So for this talk, I stuck with a fail, right? And for this talk, my answer has to be yes, your meta theorem would hold, even though you did everything wrong and failed at everything, right? But what you should do is produce precise errors, you know, that then allow you to identify within the logical relation that, you know, when something is a legitimate error versus just fail. That way you can be much more precise in terms of what parts you're ensuring static safety for and what parts you're not as well.
So are failures going to be returning proof trees, deriving bugs or something?
Well, for now, I was just, we were just playing with having a precise error that allows you, you know, we want it to map to something that's happening at the source level. It's not quite a proof tree.
Okay.
But yeah, but that's a very good point.
Thanks.
Can I continue that just slightly, which is, so this is, I was thinking, so you went general and talked about many source languages, many target languages, etc. And I think you've got some real sense of how the compilation, what sort of things have to be preserved, what's going on in order for this to work. And so there is some sort of general assumptions around, even though you're in the special case at the moment of simple examples.
Yes, exactly. We're doing the simple examples to test out different scenarios of different flavors of languages, different flavors of compilation, how low level your target is, and so on. We haven't done incredibly low level targets yet. Doing this all the way down to cherry would be really hard. That's why we're sort of trying to design like a lambda calculus-y version that does capabilities.
Thank you. Phil?
Right. That was a really nice talk. I really enjoyed that. And very often you work with stuff that's really quite complicated and hard for me to follow. Right. Lots of our colleagues are like that. So you mentioned you only had 20 minutes. You had to pick the simplest possible thing. We should be putting those restrictions on ourselves much more often, because this led to a really beautiful talk. I think it was very easy to follow.
All right, great. Thank you, Bill.
My specific question was, you used this thunk trick, and you used it at two places. You used it for interop. Obviously, you have to use it at points of interop. And then you also used it to compile the affine type language down to the untyped target language.
Yes.
But the affine language is typed, so it's already guaranteeing that you're not,
yes.
to avoid using the thunking there.
Yes, absolutely. Okay, so again, this was just because it was a simple talk. That part really bothered me as I was making the talk, because I had morphed the. So what's the issue here? The problem is, you're absolutely right that if you have an affine function written only in affy and it's completely orange, right, and you type checked it, then you know statically that there's no way that this function is going to use its argument twice. Why the heck are we thunking those arguments, right? And that's exactly what we ought to be able to get rid of. Now, how exactly to get rid of that? I think that what happens is that you kind of have to do something in the surface, interop FFI design to mark where you essentially are polluting your affine types, right? You can think of it as a modality if you like. There are genuinely affine lolly functions, and then there are things that may not be, that might have some blue function hiding underneath, which is not going to do a good job. And then if you could do that, then you definitely get the benefits of static enforcement for all the things that are statically going to make sure that things are used in an affine way.
I see. So yeah, I'd like to see that carried through, because I didn't quite follow the details of that. But it'd be nice to see that carried through at that simple level as well. I look forward to seeing that.
All right, cool.
Okay, thank you, everybody. I think we should stop there and have our break. If we can have Amal's unshared, yes.
Yep.
Now, so here we've got the break. I am moderator, so I am working hard, so I'm going to get a cup of tea. But please put your videos on, say hello to each other, and use the break well, or get your cup of tea.
Can you all see my screen?
Yes, we're fine. So let's get started. Hello, everybody. So Viktor Vafeiadis is a researcher at the Max Planck Institute for Software Systems, and he's working on the semantics and verification of concurrent programs, especially under weak memory consistency. Now, I've known Viktor for a long time, since PhD times. I have never seen him so hairy. Please get going, Viktor.
Yes, well, thank you for the introduction. Thank you for organizing this workshop, for all being here, or remotely here. But my talk is a bit strange in that, like a politician, I'll start with a bold statement. Let's make stateless model checking stateless again. It's perhaps not as catchy as some of the statements of politicians, but at least it's not so devoid of meaning. And through the talk, I'll try to explain what I mean by this. It will contain a small lie, but I hope you'll forgive me about it. So what is model checking and what is stateless model checking to start with? So very, very basically, you have a program P and a property phi, and you want to check that all the executions of the program satisfy the property. So for this talk, I will be considering concurrent programs with shared memory. And as for properties, I would be considering safety properties. So the program does not crash. Any assertions embedded in the program are satisfied. So the basic approach, you try to execute the program in all possible ways. And for each such execution, you check that the property is satisfied. There are three basic approaches for doing this. One is explicit state model checking, as practiced by model checkers like Spin, where you explore you try to explore at least the entire set of reachable states from the initial configuration of the program. And while you do so, you store this set of reachable states. And so that you can make sure that you never visit the same state again and again. This works for relatively small programs. For bigger ones, you just run out of memory trying to store this huge state space. So a different approach is to use a SAT solver or an SMT solver to do the search. So you encode the program, its semantics, and the properties that you want to verify as a formula. You give it to a dedicated solver, you wait for some amount of time, and hopefully the solver comes back and tells you the program is correct, sort of the formula is sort of unsatisfiable, or that there is a certain bug in the program. Now this sort of, again, this sort of tends to require a lot of memory. And for any sizable program and sizable property, this again cannot really scale very well. So an alternative approach is this stateless model checking, which tries to explore really all the executions of the program without actually storing them. So it tries one execution of a program, then it tries another, a third one, a fourth one. And if the program is finite, so all of its executions are terminating, even terminating within a bound, then sort of at some point, this process will terminate, and sort of you will find out whether the program satisfies a property or not. So it's, in a sense, the most naive approach, but one that for certain classes of programs sort of seems to work better than the others. So the basic problem with this approach is not the memory consumption, because you just store one execution at a time, but rather the number of executions, which is huge. So especially if you have concurrency, sort of I have here I'm presenting sort of a number of threads and a number of memory accesses per thread. If you consider all the possible interleavings with these numbers, you see these numbers sort of get huge. Sort of after 3 threads, you cannot really expect sort of this naive search to terminate within reasonable time. Now, if you add weak memory to this, you'll see that even with 2 threads, or even then you quickly will not finish within a lifetime. So what do you need? You have to exploit some structure of the program in order to make the search sort of faster, to make the search space smaller, and therefore the verification faster. A standard technique is partial order reduction, or sometimes called dynamic partial order reduction. And the idea there is that accesses to different variables really commute. So if you have, let's say, the simple program here that I've displayed, where you have 3 threads each writing to different variable, it doesn't really matter in which order you interleave the threads, because all of them will return the same outcome. At the end, X and Y and Z will have the value 1. So while the naive approach would explore all 6 executions, if you apply partial order reduction, it will explore only a single execution. So now, sort of going back to the previous slide, sort of you get this exponential blow up of the number of executions, but only if the threads are all accessing the same variable. So at the extreme, if each thread is accessing only its local state, then you have a single execution. And so stateless model checking for that completely parallel program is instantaneous. So how does partial order reduction work? Very, very roughly. So the typical algorithm generates one execution trace of a program, then tries to find data races in that execution trace. And with that, it will create some new traces that it will have to explore. So I'm giving a simple example here. So we have 3 threads, one writing to X, the other writing to Y, and the third one reading from X. So let's generate a simple trace here. Let's say the threads are executed in sequence. Then what do? Sort of we notice that the first and the third statement access the same variable, so they're racy. And we'd want to generate now an execution that reverses this race, that executes the third thread before the first one. So with some extra state, you can essentially block the first thread and rerun the program and unblock it once the third thread has executed, or executed at least one statement. And so you would get this new execution here. And for this small program, that's all that you have to do. For larger programs, you would repeat this again and again. Now, to make sure that you've explored all the possible executions of the program, so that you have to keep some state as to which sort of explorations you have explored and which ones you still have to do. So once you start employing partial order reduction, now stateless model checking is not stateless anymore. That's probably all right if the additional state that you have to keep is pretty small. And now in the literature, there are basically 2 types of partial order reduction. Ones that keep a small amount of state, so small meaning polynomial in the size of the program, but which occasionally explore redundant execution. So they explore either the same execution again, or they sort of start exploring an execution that they've already considered, and they notice sometime later, so they block that exploration. So they waste some time. The alternative is that there are some algorithms that are guaranteed to never explore the same trace twice. But in doing so, they actually store essentially all the traces that they have visited. So each time you create a new one, you just check within your dictionary whether you have already seen that trace. So this generally requires exponential space. So it somehow negates the benefit of stateless model checking. Now, just before I go on and say what I'll try to do, let me just tell you that partial order reduction is hugely important. And I'll show it here with a small table with some small benchmarks taken from a tool called RMM that verifies these programs here. These are programs, I think, with 3 threads each. There are some stacks, some queues. Now, if RMM is a tool that a model checker that performs a very naive partial order reduction, so almost not at all. And so you can see even for these small benchmarks, it takes about 1,000 seconds each. Now, if you employ optimal partial order reduction, this is this other GenMC tool, then suddenly all of these benchmarks are trivial. they can be verified in less than a second. So generally, partial order induction is something that we really want. We really want it to be optimal, but we cannot afford the exponential space that is necessary to achieve optimality. So the goal of this project that I'm embarking on is to create a partial order reduction algorithm that is both exploration optimal, so it doesn't explore the same state multiple times, and also space optimal in at least it uses exponential, and it never uses exponential space, it only uses polynomial in the size of the program. And this is work in progress. So unlike most of the talks, if not all of the talks so far, I'm not reporting on research that I've finished. It's some ideas, and I would like some feedback on them. So I cannot present you the full algorithm because it still doesn't completely exist, but I'll give you some key ideas that allow us to generate an algorithm that we conjecture satisfies those two properties. So what are these key ideas? First, I'll change the representation. I will not represent executions of a program by traces, but rather by execution graphs, a concept taken from weak memory. Second, I will explore executions eagerly. And third, I will use something I call a maximal extension to avoid duplication. So let me explain these in turn. So first, what are execution graphs? They're a concept from the weak memory literature. So in weak memory, you often see programs like this, like the one here, that has some strange behavior that is not explained by just interleaving the threads of a program, but can be explained with a more complex operational semantics that has certain buffers and so on. But this is not the only way of describing weak memory models. An alternative is using execution graphs, which are the representations of single executions of a program. They're graphs, so they have nodes. The nodes correspond to the memory accesses of the program. Let's say here, if you can see the point, my mouse pointer, there is a write of 1 to X, there is a read of Y, and so on, and various orders among those. So the standard ones would be the program order telling us which event is executed before some other event in the control flow of the program. Then there is a read from relation saying for each read from which write it's getting its value, and some total order on the writes that to the same location, that's called the modification order. Now, the advantages of using execution graphs is that it makes the partial order reduction immediate. So for the simple program here that writes to 3 different variables in parallel, there is precisely one execution graph of this program. So if your algorithm generates these execution graphs, it will just generate one. It will not have to detect races and backtrack and generate others. The second benefit is that it makes all this work immediately apply to weak memory models, because all you have to do is to change the condition under which a graph is allowed by the model, something called the consistency predicate. You just plug a different definition and the model checker would work. And so the third and most important, it gives us some new insights into this established field of partial order reduction that allows us to generate better algorithms. So one is that one can coarsen the equivalence relation, one can let's say, optimize the algorithm further, but that's not what I'll talk about today. Today I'll talk about how you can sort of revisit the reads in the graph, and I'll get to it in a moment. So what is my second key idea? That of exploring the alternate executions of a program eagerly. So do not wait until the end of an execution to find the racy accesses and try to reorder them. But each time you add an event, consider all the possible ways you could add them. And this is sort of standard sort of tree traversal. So if you have a tree here of the sort of possible executions of the program, the height of the tree is really the length of the program, but the width of the tree is typically exponential in the size of the program. But you can traverse a tree, let's say by depth first search, by just storing, but just keeping polynomial space, just the current path really. So what's the key property of weak memory models that allows us to do that? It's this prefix closeness property, meaning that if you have a graph, an execution that is consistent, and you take some maximal event in it, then if you remove that maximal event, the execution remains consistent. So maximal here is in the program order, so it's the last event of a thread. And RF maximal, it means that nobody's reading from that event. Now there's a technical way, or the reason why this holds, that sort of generally consistency is defined by sort of the absence of certain cycles in the execution graph, and removing an event cannot sort of create a new cycle. So what does this allows us? It allows us to build executions incrementally. So we start with an empty graph and then add an event at a time in each possible way until we've reached a full graph corresponding to the execution of a full program. So more concretely, I will fix an order in which I add the events, let's say from threads, let's say left to right. So let's say in this simple program where I'm writing to X in the first thread and reading from it in the second, I start with the empty graph containing, let's say, only the initialization right to X. Then sort of I go on and add the first event of the first thread, and then I add the read of the second thread. Now, when I add a read, there are two options. It could either read from the initial value or from the first thread. So I'll have two sub-explorations that I will have to explore further if there were further threads. I cannot hear you, Philippa, but I think I understand. Of course, I mean, in a different program, it may be the case that you'd add first the read and after the write. And so you'd have to account for that. So suppose the model tracker were to add the read first, then when you add the write, you cannot just simply add it to the graph and consider all its placements in the modification order relation, but you also have to consider the case that existing reads in the graph would read from the newly added write. So,
excuse me, Victor, sorry, I was muted. Yes. I've stuffed up timing because I was concentrating so much. My fault. You haven't got many more minutes.
Okay.
Sorry.
So,
but take, you know, it's my fault. So take enough time.
So here, by revisiting the read to read from the newly added write, you'd have two graphs, exactly the same two graphs that you had the other way around. So when revisiting a read, you have to delete some events of the graph from the graph. Let's say here I'm giving a simple example where the first thread reads X and writes its value to Y. So if you add the write of the second thread, revisiting the read of the first one, you have to delete the write of Y because it depends on the value that you read. There are various options as to what you can delete, and different algorithms choose different ones. But in essence, you have to delete some events. So, and here comes my final key idea that will tell you when can you revisit. And this is this maximal graph extension. So some motivation. So here I have a program, again, with 3 threads. And suppose I add all the events from left to right. So and just before adding the write to X. So I have now two graphs where they differ only in what the y can read, either the initial value in the first graph or from the first thread. And now I'm supposed to add the third thread to revisit the read of x, deleting the read of y. So in both cases, you'd result in exactly the same graph. So you want to find a way to allow the revisit in only one of these two cases, not in both. And here the idea is this maximal. I'll use maximality. I would choose to revisit only in the case where the read of y reads the MO maximal, right? So the right of one. So generally, if let is consistent, then with it, it is. So in a sense, it tells you that take an execution that is correct under even whatever weak memory model. You can always extend it by adding a maximal event. So either a write, put it at the end of the trace, or a reading from the maximal one. And that is consistent. And using this property, now you can consider sort of the deleted events that would occur from a revisit in some fixed order. And now, if you ensure that along that order, all these deleted events were added maximally, then you would get exactly one execution, and that execution would further be consistent. So that, and those two properties are what would guarantee the soundness and optimality of the algorithm. So to summarize, I've sketched at least an algorithm that I claim is sound, complete, and exploration optimal. It would use only polynomial space in the size of the program. Polynomial, and actually quadratic. Why is it quadratic? Because each sort of you have sort of possibly a linear number of revisits. That's sort of the number of writes in an execution trace. And for each level, you could be potentially storing an entire execution, which is also linear in the size of the program. And because all of this is all the sub explorations are really independent from one another, this can be easily parallelized. So with this, I would finish. I'd caution you that it's work in progress. So I haven't proved all the theorems that I'm claiming are true. And I'd like your feedback.
Thank you, Viktor. Great talk. Thank you very much. There's some questions. So I'll first go to Andreas and then to Azalea, who's got her hand up. So first, Andreas.
So in the goal, you state two sub-goals, and one is in terms of a complexity bound, and the other one is referring to an ideal situation, like no redundant. Could you replace the ideal goal by a complexity theoretic goal? Because that's what we care about, right? I mean, why is it so important to have the optimum or the ideal situation that there is no redundant exploration?
Okay, fair enough. That's not necessary, but you would want to bound at least the wasted explorations to at least some polynomial factor.
Exactly, yeah.
So, I mean, the current algorithms that I'm aware of are all sort of essentially unbounded, so they're exponential.
But there might be some middle ground, right? Between exponential and not ideal.
Yes, very much so. Though I hope really that I will be able to solve this this ideal case, in which case we wouldn't need the middle ground.
Azalea.
Thank you very much, Viktor, for a great talk. So two questions, one very quick. What was the lie you told us? And two, so in terms of this property that it required, the maximality of PORF, RB, and MO, ignoring memory models that allow load buffering, what else can you say about memory models that do satisfy this property, this maximality? Which models do satisfy it?
So for the second property, I think that sort of all the known models satisfy it. The idea is that you can sort of, in an operational fashion, you can execute the program after any point in a sequential, consistent fashion for that extra event. Exactly. And that's always possible. As for the lie, well, okay, it's quadratic space, so it's not really stateless.
Okay, thank you.
Sorry, Tony?
Oh, I just had a question.
Okay, Tony, then Peter, and I'm thinking that Madhususat Dan is not wanting a question, unless he said something. So Tony first.
I'll pose it as a question. Do you know of Jad Algav's work on the tool Herd?
Yes.
And she has something very similar with the from read.
Yeah.
The FR being RF backwards.
Yes, so the memory models we use are the same, the memory models that Jad Algav has in her tool. It's just that it's her tool for exploring all the possible execution of a program is not really optimized for speed. So it's really has a very naive exploration strategy that is exponential.
Thank you very much.
Pete Saul?
Hi, Victor. So that was very nice, as ever. But as ever, I'm curious what one can say or what one might hope to be able to say about the hardware models that permit LB behavior.
Yes, so the precursor of this, so GenMC, also works with hardware models that allow sort of, let's say, constrained load buffering behavior. So with some preserved program order, union RF being acyclic. I expect that this extension here, or this better algorithm, will also work for those, but I haven't worked out the details. Essentially, in the development, you will have to replace the program order with a preserved program order.
Yeah, okay.
I think in the interest of time, we should leave it there. Thank you very much, Victor. Please, can you, yeah. And hello, Artie, I can see you there. Are you ready to share your screen?
Let me do that. Does this work?
This works, yes.
Great.
Thank you. So I'll introduce you. Artie Gupta is professor in the Department of Computer Science at Princeton University. Her research interests are informal verification of programs and systems, automatic decision procedures, and electronic design automation. And I've talked to Artie just a bit in conferences in the past, and sort of in more recent work, I've been looking at some of her work and going, oh, has she done this? Oh, has she done that? So I'm actually really delighted that she's giving a talk here today to find out more.
Thank you so much, Philippa, for that introduction. And hello, everyone. I'm really happy to be here and talk a little bit about the stuff I've been doing for network verification these days. And the talk today is about actually using abstract interpretation, which I'm sure many of you love. So, okay, I don't know if I can advance. Okay. All right. So networks, provide very critical infrastructure in society today. They connect us to the software services we love. And of course, they've been lifesavers in these tough times that we're all going through. So for a network, it's useful to think about the way it operates is that there is a control plane where you have these various routers that are talking with each other in a distributed manner, and they are essentially executing some kind of a protocol, and they are configured to take messages from each other, choose some routes, and so on. And there are various control plane protocols like RIP, OSPF.
Yes.
We can only see the title slide. So can you?
Oh, okay. Let me try.
I've had this problem before. If you share PowerPoint, the movements are not seen by the audience, but if you share your desktop and then you enter the screen, and then it will be okay.
Okay, let me try sharing. So where should I pick the desktop? Oh, I see. Can everyone see the slides?
Can you test? Can you test? Go back and forward. Yeah, we can. It's changing.
Okay. Hopefully it'll work. Yeah, thanks. Right. So yeah, the slide I was talking about was this one, where you can think of the network as having essentially a control plane where routers exchange messages with each other according to some predefined protocol, and they are configured sometimes with like hundreds of thousands of lines of code that everybody is very afraid to touch. But essentially, once the control plane protocol is done, what you get are forwarding tables, which constitute the data plane of the network. And these are essentially rules about if you see a packet that is destined, with the destination going to this address, send it to port 1 or send it to port 2 and so on. So these are just forwarding tables. And these are what determine the communication of the packets and the runtime. When you see a packet that is headed for a certain destination according to the header field, you will send it out. So network errors, sadly enough, are very common and they are very disruptive. It's because you do use these software and actually really low-level software in the configurations when you are trying to arrange for the control plane protocols and the rules that need to be followed also in the data plane. So there has been a lot of interest in verification, applying formal verification like techniques. So the graph here is sort of trying to give you the landscape, if you will, of the various efforts that have gone on in about the last decade or so. So on the x-axis here is the coverage that you can see. So earliest techniques like ping or traceroute look at a single packet and see where all it has gone. Once there were interest in looking at data planes, especially in the context of software defined networking, some of these techniques like HSA header space analysis and Veriflow have become very useful in verifying properties like reachability, but they do it for a single data plane, which means for a given set of forwarding rules, you can verify whether you have the properties or not. Of course, there's been interest in also verifying the control planes. And so there you look at all possible data planes that might arise out of the control plane because of the configurations. And there are work which have looked at particular kinds of abstractions for those. And some of them can actually handle all possible data planes because they're doing symbolic analysis like Bagpipe. So a few years ago, when I started working in this area, I, of course, love SMT solvers. So the work that we did in Minesweeper and Bonsai was essentially modeling the control plane behavior of a network using SMT models, using SMT constraints. And then one could verify in the usual way any property and find a violation. But the work I'm going to talk about today is Shapeshifter, and this was presented at Popple last year. This uses slightly different techniques. And before I tell you about more of that, let me tell you what is going on in a generic routing protocol. And this was stuff that I learned when I was trying to figure out, how to model the control plane behavior. So here we have a very simple toy example, let's say with just 5 routers. Let's say one of them is actually the destination. And I'm going to show you how a idealized RIP protocol, routing information protocol, works. So you start with the origin or the destination, creating an initial announcement stating that it has a path to destination D. It's obviously D. So let's say that the distance to destination here is 0. That's what the protocol is going to maintain, the distance to the destination. And once there's an announcement, the nodes that receive the announcement will pass it on to their neighbors, possibly modifying it. So here, when we transfer this announcement, the distance now becomes 1 at each of these neighbors, and the nodes will keep doing that. They will receive announcements and they will send them on to the neighbors. And if there are multiple announcements at a node, for example, here, they will use some logic, which is configured in the protocol to choose a best route. So here, actually, the distance for both of these announcements is 1. So it doesn't matter which one you choose, but let's say then you would choose one of them, and then the distance to the destination becomes 2. And at this point, for a tower example, there's nothing else to do. And so eventually, hopefully, these protocols are designed so that the system converges to what is called a stable solution, which means even if you get more announcements from your neighbors, you are happy where you are, you don't change your announcement anymore. So all of these routing protocols are essentially designed, if they are well designed, to result in stable solutions. The problem, and this is what we had done when we wanted to model the behavior of the control plane in terms of an SMT formula, we essentially modeled a formula such that its satisfying solutions gave us stable solutions. However, the problem is of scalability. Whether you use control plane simulation, and there have been past efforts that use that, in particular, Badfish is a really, really nice tool that does the job of taking a lot of vendor languages in which the configurations are specified and extracts a logic-based model from it in order to perform simulation. Our work, Minesweeper, had done control plane verification using SMT, and there have been other methods also that use various abstractions to talk about control plane verification. The problem with most of them is that they scale up to, let's say, about 1,000 or so routers, but we are faced with data centers that have of the order of 10,000 routers. So the scalability challenge is huge, and those of us who work in verification know that's always the essential bottleneck, whether it's hardware designs or it's software programs. For networks too, it's really the scalability that's a big problem, especially if you want to handle the control plane and all possible data planes that arise from it. So as usual, our answer to it is to use abstraction. So we'd like to leverage abstraction to combat the design complexity, in particular for proving the kind of properties we are interested in, which are essentially about reachability and so on. So what we did in this work was we formalized the theory of abstraction for routing protocols, where we combined the well-known abstract interpretation techniques due to Cousteau and Cousteau with the theory of routing algebras. And actually in the field of networks, the routing algebras have been very well known due to Sobrino, Griffin, and many other people. What we did was combine the two, and this is, this was presented, as I said, in the Popple 2020 paper. Let me give you the essential intuition behind how we used abstract interpretation along with the theory of algebras. So in terms of just a one-slide primer on what is a routing algebra, we are given a network topology. Let's say the V, the set of vertices, are the router nodes. The edges is the connectivity between them. Just because you have an edge doesn't mean that you're going to always accept to send your packets on that edge. That's really what the routing protocol determines. So we have an algebra, which is a 5-tuple. S is just a set of routes that are getting exchanged between the nodes and the vertices. Merge is a function which, given two routing announcements, tells you which is the one that you're going to choose. So it's like choosing the best or choosing the preferred one amongst the announcements that you see. And we can define it pairwise and of course apply it to all the announcements that are seen at a node. Transfer is this function which tells us how along an edge, given an announcement, you may do some modification. So as I showed you in the previous slide, if you get an announcement with 1, then when you send it out, it will have distance 2 plus 1 on it. So that's the transfer that happens when you send an announcement to a neighbor. And for the boundary conditions, we've got an initial route. Let's say we denote it by a 0, but it's in some sense the the initial value, and an invalid route, which is lack of a route because maybe it gets dropped or maybe you didn't get any announcement at all, is denoted as infinity. So this is a very nice algebra, and many properties of such algebras have been studied. And in fact, it was shown that many routing protocols can be seen as following some algebra, and then you can reason about things like convergence and so on. But what people hadn't done so far was to use these algebra along with the topology in order to check properties like reachability or other properties that one may be interested in. So let me give you, rather than go into the theory of it, which you can read all about it in the paper, I will give you a bit of a hint. Let me show you by example how we can use an abstraction with a routing algebra. So here is again a toy kind of a network. It only has 5 routers. Let's say R1 is my destination, and R1 is connected to 2 routers here. The edges on the labels on the edges show what happens to an announcement. So if we send an announcement from R1 to R3, we will add a community tag called C1. And this is the kind of thing one might do in a protocol called border gateway protocol. And actually, I'm showing you a simplified view of it. But essentially, it has community tags and so on in the routing fields. So you can add and remove community tags, and you can even have conditionals over here. So if the community tag is 1, then the local preference, that's another route field that is maintained in BGP, is assigned to 200. The local preference in general as default is 100 in a BGP protocol. So all that is happening in this network is if you transfer an announcement from R1 to R3, you will add the tag C1. And along this edge, if you send the announcement from R3 to R4, if there is the tag C1, then you will change its local preference to 200. So you can think of it again as the program, the announcements are being exchanged between these routers, and you're doing transfers and so on. So let's say for this particular one, I can model the simplified BGP as really where each announcement just consists of a local preference, the path that I have, and the community tags. And the transfer along each edge will simply add the sender to the path. And it might, for example, set the local preference to something like 200, as is shown over here. So let's see at the bottom what would happen when such a protocol would run using, let's say, this routing algebra. So to start with, the destination says that the local preference is 100, which is default. There is no path, so this is the origin, so that's why this is empty. And let's say that the default for the community tag is that it starts with a 0. And then when I go along this, the announcement will be modified. So now R1 will get added to the path, and the tag C1 will also get added to the community tags, and so on. So here I would get 100, R1, and 0. And from these two, when the announcement comes here, you can see that the path would get extended by adding the sender here. And here is where we choose first, the best route. And BGP usually chooses something with a higher local preference. So because along this edge, the local preference was changed to 200, so R4 will prefer the path sent from R3, and therefore R3 will get added to the path, and the tag will also be the one that it receives from R3, not from R2. And once we have something at R4, it will simply pass that along to R5. And at this point, we've sort of converged. There are no more changes that might happen because of the transfer of announcements. Let's see what happens if we try to abstract these messages. So some of this computation on adding the senders to the paths means we will maintain longer and longer path lengths. The local preference might also be choosing the best among them, might be expensive. So what if the user or network administrator doesn't really care which path I have from R5, as long as I have some path to the destination? So one could think about abstracting the routing messages. And suppose we abstract this message, so we now keep only a simple reachability marker, which says whether I have a route or not. And I will also keep just the community tag. And in fact, I will use a ternary representation. Sorry, this should have been a closed paren. I will use a ternary representation for the community tag. So I will keep 0, 1, or star. Star means I don't know which one it is. It could be either 0 or it could be 1. So if I use this abstraction now, I can play that same game of transferring the announcements, but this time I'll be operating on an abstraction of the routing messages. So I would start
Excuse me.
Yep.
So a bit less than 5 minutes, please.
Okay, no worries. Thanks. So I will start with, the announcement that at the destination, it's reachable and the community tag is 0. And this time I'm not going to save the path length or anything. So my abstract messages that I will save get at R3 and R2 as shown in red over here. The interesting thing happens at R4 because I get a message with the community tag 1 and I get another message with community tag 0. And because I'm not saving which one it is, I will abstract it and perhaps lose some information. And with that uncertainty, I will save it as a star. But now I still get a star at R5. And because the reachability marker is 1, I do know that there is a path that can reach R1. It's just that I don't know whether the tag will be 0 or 1, but it's okay. So that's the essence of the abstraction that one can do on the routing announcements. And I won't go into the details, but we essentially talked about abstract interpretation with respect to these routing algebras. And by using many of the properties that arise in networks, we were able to show soundness theorems, which essentially said that if you do your simulation or your execution with respect to the abstract algebra, and if it is uniquely converging, then for any asynchronous schedule, which means we don't have to even worry about the message orderings, we proved that working with the abstract algebra is sound with respect to the concrete algebra A. And of course, as you know, abstraction has many key benefits. In particular, for networks, they often give precise answers. And I will show you that on our experiments, we got precise answers on 95% of real networks. They improve performance a lot because you're tracking much less information. You have smaller state space, fewer iterations to converge, which takes less time, and it creates opportunities for sharing, for example, for multiple destinations. And we also used abstraction to enable new network analyses, for example, a potential hijacking analysis. And here's a very simple example. If we have a network connected to 2 different external ASs, and let's say suppose we abstract the path just to keep whether something is an internal route announcement or an external, then we can use the same game to just keep track of internal or external. And at this point, at this node, when we do a merge from something that's external and something that is internal, we can find that because of the external label appearing in the map that we are saving, it's a potential hijacking attack. So with a very simple abstraction, one can actually detect potential hijacking attacks. So we created a tool called Shapeshifter where we abstracted some common things, especially for BGPs. I won't go into the details, but let me just show you that we were very surprised and pleasantly surprised that on real networks, we were able to finish the abstract simulation in less than a minute on each of those networks, which was 1 to 2 orders of magnitude speed up over batfish, which is sort of the state of the art in terms of network simulation. In fact, about half of the networks had more than a 50x speed up. Furthermore, we could prove soundly the reachability for all destinations for about 95% of the networks, and for the remaining 5%, we could show reachability for the majority of destinations. So this was great. Asymptotically also, it was good to see that we got many orders of magnitude improvement over doing concrete simulation for data centers with increasing size. And here is a slightly more detailed graph that shows the times for concrete simulation versus different kinds of abstract simulations that we use with different abstractions. And again, the details are in the paper. But let me just conclude to say that in this work, we formalized the theory of abstraction for network control planes, where we proved soundness for all asynchronous concrete executions. And we built a tool and evaluated it on production data center network, achieved high precision with very few false alarms, and we checked connectivity and variants that are of a lot of interest to network administrators. Thank you.
Thank you very much. So I have a question to start us off.
Sure.
I was actually surprised. So, I'm not from your field. You've got these simple networks and you're doing these simple abstractions. Then you went from there to what in 95% of cases you can do it. So what's actually going on with these networks in terms of, are they very simple? And the flip question is it difficult to find these abstractions for these networks, and how does one have to think about this?
Yes, that's a great question. And I have to admit that we were surprised too. In particular, we thought this was very surprising. And even that 95% of the network, actually, we were able to prove reachability. So these were data center networks, which are very structured. They have like a fat tree topology. And I think the main reason that we were able to prove correctness is because there's a lot of fault tolerance built into the kind of configurations people do for these, so that reachability from one to any other, in the network is very important. But because there's multiple ways that faults could happen, it doesn't matter which path you're taking. So I think that is the essence, because our abstractions ignore the part where we are computing the best path. But as long as there is some path for reachability, yes, and because we are approximating it soundly and pessimistically, what is interesting is that even then we did not get many false alarms. In fact, I would say, what are the 5% of networks where we weren't able to prove? And there they were using more fancy features like regular expressions and other things to, basically perform the best route announcements or the route filtering and so on. Yeah.
Thank you. And there's a couple of questions in chat. Adam first.
I was just curious if it's possible to notice patterns in subnetworks of a large data center, so that you don't need to do a global analysis here, and you wouldn't need to see a superlinear scaling as the network size increases.
Excellent question. I have a student working on modular verification techniques, because the way these data centers are built, let me see if I have a picture here. I probably don't. But, there's like the pods, and then there's the aggregation layer, and then there's a core layer. And oftentimes the policy for the network depends on the role of a router in that structure. And so one could, in fact, come up with a way to define what the policy is, or convert that into a specification of what you want that policy role to be. And that's a great question. So in the past, in our bonsai work, we actually used the symmetry to talk about a compression of the network, where we essentially, we conducted a homomorphic bisimulation kind of abstraction on the structured thing to get a smaller model on which we know it is sound. So that perhaps answers your question. But taking that even further, creating modular verification opportunities. Yeah, I have a student doing that. It's work in progress.
Great, thanks.
Thank you, Adam. Sanjeeva?
Hi, Aarti. Thanks.
Hi, Sanjeeva.
Great talk. How are you doing? You partly answered one part of the question when you answered Adam's thing about the small model, but a couple of questions which I had. I don't think Tim is around today, but did you use abstract interpretation for discovering any of the invariants about the network structures and protocols? That was the part A of the question. And does this work well with composing one network with another? Sabrino and Tim Griffin have used some stuff using semi-modules. Very nice algebraic work.
Right. So I think the work of, multiple protocols sort of being used in composition can be easily handled with this SRP model, which combines the topology with the routing algebra. And actually, Ryan Beckett, who worked on this particular tool and did some past work, has ways of combining that. So I think the composition part, because of the formal algebra and so on, works out quite nicely. Your first question, which is, have we used abstract interpretation to find the invariants? Actually, so far, our abstractions have been targeted very much only for reachability. So, it was really for fast reachability analysis. So it would be very interesting to think of what abstractions might be useful for other invariants. So like I mentioned in another student's work, there we are actually using the SMT-based formulation because it's just more expressive. We don't have to worry about whether or not we would get the precise answer. So I'm actually using more the SMT-based models there for finding invariants because I don't want to worry about whether I have the right abstract domains or not.
Yeah, maybe the protocols you're looking at aren't that challenging. Lenore, Zook, and I were looking at protocols which had mobility and stuff which had like core networks where reachability is a much harder property to prove.
Absolutely. And you're absolutely right. And I'd love to maybe catch up with you on some of those things. I think of those as, so we went after the standard legacy distributed protocols, and BGP, I have to admit, is one of the fanciest ones we have seen. And it's also crazy because everything that we have thought about works on OSPF, works on RIP, but BGP has this twist always that you have to sort of handle because of this, in some sense, non-monotonic preference order that it has.
Thanks.
Okay, thank you. And now the last question. I'm very sorry, I can't pronounce your name very well. Zelkang or something.
Hi, Zelkang.
Sorry.
It's okay. Hi, thank you, Aarti. Very nice talk. So the selection, so the routing algebra will select a single best path for now. I'm just wondering, will it be able to adapt it or to support multiple path selection? So I'm working with my colleagues on traffic engineering. So you have to take multiple paths to split the traffic, and you may have to explicitly make the decision how much traffic will go through which path.
Right. So I think our techniques can be possibly extended because really in our implementation, I don't know if you can see the screen, we essentially keep maps, so for different prefixes. And if you wanted to keep multiple paths for the same router, that would be possible also. In fact, a lot of this can be embedded in general in NV, which is a platform that my colleague Dave Walker has developed with his students. It's actually a domain-specific language embedded in OCaml. So it's very expressive. It allows you to use the, whatever kinds of maps and other data structures that might be useful. So I think the algebra would extend to that. You'd have to be careful about defining, the compositions and if there's some place where you need some resolution.
Right. Very nice. Thank you.
Yeah. Thank you.
Thank you. I think we should stop there. Thanks very much, Artie.
Thanks so much,
for your
everyone.
talk.
Thanks for the
Thank you.
feedback. Bye.
And our last talk today is Alexandra Silva. Would you please share your screen, Alex? And while she's doing that, I will introduce. So Alexandra Silva is a theoretical computer scientist whose main research focuses on semantics of programming languages and modular development of algorithms for computational models. A lot of her work uses the unifying perspective offered by coalgebra, a mathematical framework established in the last decade. Alexandra is currently a professor at University College London, and she will start a new position at Cornell sometime later this year. So sometimes I reminisce with Alex and say, do you remember the time we went dancing in Brazil? Well, now I'm going to, in future, talk about, do you remember the time where we met during COVID? Alex, please give your talk.
Thanks, thanks, Philippa. Can you confirm that you're seeing my full screen?
I can see your screen. Do you want to test it? Yeah, it's fine.
Okay, thanks. Yeah, so it was nice that Artie motivated already network verification in her talk, so I can sort of probably skip part of my motivation. But the work I want to show you today is joint work with Boris D'Antoni at UW-Madison. So I spent COVID year in Madison on sabbatical, and this is really the result of my year there. It is the work of an undergrad at UCL, Tiago Ferreira, and a lot of the results you will see are actually implemented and done by him. So it is also great that undergrads get involved in research, and I'm very proud of this particular result. And it is also joined with Harrison Bruton, another undergrad at UW-Madison. This will appear at SIGCOMM later this year. So it's about black box analysis of network protocol implementations, and it's about a tool or more a tool framework that we developed called Prognosis. But before I go into the sort of practical aspects of the work, I will spend about 5 or 6 minutes talking about the theory side. So since the workshop is from theory to practice, I would like to spend a little bit of time on the theory side of things. And sort of the broad context of this work, one can say it's at the space of at the intersection of semantics and verification. So one can think of semantics and programming language semantics as trying to answer the question, what does this program do? And then one could think of the verification side of things as trying to answer the question, does this program satisfy a certain list of requirements? And what is really beautiful about these two research lines is that in many cases, they are actually two sides to the same coin. And I'm saying this, and there's actually a very precise meaning to this metaphor. And in a lot of the things I will show you later on, and I'll try to point this out, for the people in the audience who are familiar with duality theory coming from algebra, there's a lot of duality going on in a lot of the theoretical tools we use in the verification side of things. And I find this actually a really beautiful part of this work and some other work I've been doing. So let's make this a little bit more concrete. So let's imagine we have some high-level language where we're, for instance, programming a network. In Artie mentioned NV, for instance. That would be a good example of a high-level language. Another high-level language for networks is, for instance, Netcat, also developed by Nate Foster and Dave Walker and some other people at Cornell and Princeton. And so this high-level language is given semantics through some mathematical object, which I denote by sigma in my slides. And then if you're describing, for instance, a network, you might have a series of system requirements, including some reachability properties you want to have for that network. And you might describe those requirements in some logic or some formal language, which I denote by psi here in my slides. And then the idea is that if you have a high-level language and you have a precise notion of semantics, and if you also have a formal way of describing your system requirements, hopefully you can combine these two objects and you can assert that a certain program is bug-free, or at least a certain part of the program is bug-free. But things are not always so straightforward, and sigma and psi are not always simple to handle. So they might be very complex mathematical objects. So what happens in general is that there will be something in the middle to help. And in the work I want to talk about, this object in the middle is automata. So automata are very simple, simple structures, and they can be used both on the semantic side and on the verification side. And they sort of form the bridge between these two worlds. And you can think of them as sort of translate.
Have we lost Alex? Have we lost Alex?
It does sound like it. Yeah, it does sound like she's frozen. So
let's just wait and see if she comes back.
She says that her Zoom crashed. She's trying to reconnect.
Thank you. Hey, hello. We can't hear you.
Can you hear me now?
Yes. Hello.
Yes, sorry, Zoom just crashed. I guess this is. Let me see. Can you see my screen?
Yes. And you were on the automata bit.
Yeah. I still remember. Okay, thanks, Philippa. Sorry about that. Hopefully it won't happen again. So I hope you heard the part in which I said that automata are sort of bridges between semantics and verification. And they underlie a lot of the tools that are used in program analysis and program verification. So one example of such tools or collection of tools are model checkers. And the idea behind model checking is that you have a model of a system, perhaps just a system component or perhaps a protocol. The picture I have here on the slide is a model of TCP. And you have some properties that you want to check. And the model checker will either tell you whether a certain property is true, or if the property is not true, it will give back a counterexample or a trace in your model, in your automaton model, that tells you where you can replicate your bug back in the real system. Now, this picture is very nice, and it has been successfully used in a lot of program analysis and program verification. But it assumes you have a model. It assumes that someone has designed a good model, and it assumes that someone has maintained a model of a running system. And so the question, is, do we have such models? And in a lot of the times, and in software that is constantly changing or protocols that are changing, such models are not possible to design and maintain. And it's a very time-consuming task, and it's a task that has to be done by experts. So people who really understand what they are trying to model. So a lot of the times, development teams will not take the time to design these models, and therefore they cannot apply model checking. So here's where model learning comes into play. So if we don't have a model, but we have a running system. Can we build a model? And so model learning is an area or a technique that advocates that indeed we can actually build a partial model of a running system. We can treat the running system as a black box or as a closed box, and we can interact with the system in a way that we learn fragments of the system guided by perhaps a property we want to check, or guided by some alphabet that tells me how to interact with the system implementation. And then we keep refining and updating the model. So if the system implementation changes, we can say during the night, run the learning process and update the knowledge we have of the system. And what is really nice about model learning and all of the algorithms that are out there is that this is a fully automated process. So there's very little input from the human in the process. And therefore, you can run it and you can use it without knowing too much about what the implementation is actually doing. And so here is where sort of the work I want to show you today appears. And before I do that, I want to show you the simplest model learning algorithm. And I want to show you the algorithm. I want to show some components of the algorithm. I will mention where this duality thing I mentioned in the beginning plays a role. And what I would like to, the message I would like to pass with this slide is that this algorithm is the simplest thing you can imagine. So the thing it learns is a regular language. So this is as far as it goes. So you learn a minimal deterministic automaton accepting a certain unknown language. And how does that work? So there is a, so the algorithm assumes that there is a teacher, and this teacher knows everything and knows what language the learner is trying to guess. And this teacher can answers two types of questions. A membership query. So you can ask, is a certain word in the language? And the teacher will say yes or no. And at some point, maybe you think you've asked enough membership queries and you think you can guess what the language is. So you can ask the teacher, is my guess correct? So you give your guess in terms of an automaton, and the teacher will either say, yes, your guess is correct, or it will give back a counterexample on why your guess is incorrect. And the way it works, the inners of the algorithm depend on this thing called an observation table, so this data structure, where basically you store all the results of membership queries. And once you do an equivalence query, you can refine your observation table in a way that you get an automaton in which you've seen progress. So your equivalence query will give you a counterexample, and your observation table will be refined in a way that the next automaton you guess will definitely be less incorrect. And what is crucial about this data structure is that the table always corresponds to some minimal DFA. It might not be the minimal DFA you're looking for, but it's the minimal DFA of some language. And that's sort of important for determination of the algorithm. And the notion of membership query and equivalence query are indeed dual in a very precise sense algebraically, in the same way that there is a duality between words and languages. And this is something that actually the algorithm explores a lot. So here is where we move from theory to practice. So there's this algorithm, and it's cute. It learns a regular language, but it makes some pretty unreasonable assumptions. It assumes there's a teacher. There's an oracle that knows everything about the world. So at this point, you might think that this is the sort of algorithm we teach in theory of computation, and we never look at it again. But what is fascinating about this algorithm is that it found its ways. So this was introduced in the 80s by Dana Angwin, and it found its way to verification in the last decades. And it was used in really interesting application areas. So one thing it was used for, and that is relevant for this talk, it was used to find a bug in a TCP implementation inside Windows 8. And here is a paper from 6 years ago in which they combined model checking and model learning to analyze TCP. It was also used to learn error traces And this was again a combination with model checking, in particular bounded model checking. And it was also used to actually automatically create models of the protocols that run inside the chips in debit cards and credit cards. So it is a simple algorithm, but it can be used to do some cool things in verification. In particular, with the potential of combining it with model checking and bounded model checking. And so you might wonder, can we push the theory further in a way that L-star can do more? And I think yesterday, for those of who were here yesterday, Anka gave a talk in which actually she showed an extension of L-star to concurrency. So can we use L-star to do concurrency? And I think Anka showed you that there's a positive answer for a certain model of concurrency. And one can ask about, the algorithm design, the data structure, the observation table is very simple. There have been optimizations. Can we do better? Can we even make the algorithm more efficient? And can we extend that for things with concurrency or with quantities? That's not what I want to do in this talk. In this talk, I want to say, let's keep the theory as it is, and let's try to design a tool that can use this simple algorithm in a lot of different applications. And so here is the architecture of the tool we developed called Prognosis. So our main sort of desiderata for this tool is that it can be used by programmers that don't know much about model learning. Perhaps they don't even know much about model checking. And they might not even know that much about the protocol they are trying to analyze. So we would like the tool to be such that people with a bit of knowledge of each of these things can very quickly get to use the tool. So the tool is comprised of 3 modules. The analysis module and the learning module are standard techniques from verification. So for model learning, like L-star, it has an implementation of L-star. It has an optimized implementation of L-star called TTT and some extra things. And then the analysis module has connections to model checkers, has equivalence procedures for simple models, and it also has a few synthesis algorithms that we will use in bug finding later. I'll show you an example. Now, the core of the tool is the system under learning. And so the system under learning is the implementation one wants to analyze. And more crucially is a component called the adapter. And here is the only place where the user really needs to work a little bit to get the tool up and running. So let me show you an instance of this so that this becomes a bit more concrete. So the system under learning is the implementation, so that's sort of given. But then there's this adapter component that is supposed to function as a sort of bridge between the other modules and the implementation. And this adapter, so you can probably see that if we would let the implementation communicate directly with the learner, the learning process would be, in many cases, not feasible because the implementation has too many details. So the things we're going to be using the learning process to look at are specific areas of the implementation. And so the adapter is going to be doing exactly that. It's going to be taking concrete input from the implementation, concrete input and output, and is going to transform it into some abstraction to send to the learning and the analysis module. So for instance, take the handshake. So imagine that you have an implementation of handshake in TCP, and it looks pictorially a bit like that, but imagine you have code that is basically doing what is depicted in that picture. Then the concrete symbols that you want to see are TCP packets, and they look, so this is an example of a TCP packet written in Python, so it's a record. And then the symbols that you're going to be passing on to the learning module, those will be much simpler. So they will look like abstract symbols from an alphabet, for instance, like the one I displayed here.
Alex, you've got 5 minutes, and
okay,
please,
thanks.
People ask questions. Thank you.
Okay, I'll wrap up. And so what happens is the tool takes this, so the user has to provide this translation between concrete and abstract symbols. And this is done, I should have said that, this is done by taking a reference implementation of your protocol and do a few annotations. And this is sort of the key difference with a lot of the previous work. So we assume that the thing you're trying to analyze might have different implementations lying around, and we don't assume anything about the reference implementation, whether it's correct or not, it's not relevant. But the user basically provides this abstraction function by annotating in the reference implementation which parts of the reference implementation he wants to analyze. And that's a sort of easy thing to do, which is a bit tedious. And so once that is done, then an implementation like the handshake of TCP, you press a button in the tool and you get out an automaton that looks pretty much like the thing I show on the left here. So it has 3 states and it tells you which symbols were sent around. And it has you see that the symbols, the abstract symbols have some interrogation marks. And this is what the learning module outputs. Later on, if you want to do finer analysis, you can use more knowledge that you have about your alphabet, and you can actually synthesize the constants that are passed on in these abstract symbols. And that's what you can see on the right in the slide. And so since I have 5 minutes, I'm going to skip part of the next slides, but let me just make a couple of comments about TCP. So TCP is not a very, very difficult protocol. Is relatively simple. So actually, we were able to learn an almost complete description of TCP, which was possible also because we had previous work and we knew exactly what the model looked like. But there are protocols that are harder. So there's a new protocol called QUIC that was developed at Google in 2012, and it has only been submitted as a standard in 2015. And QUIC is now very popular. It has replaced a lot of the transport layer in the internet. And there's a lot of implementations around. But QUIC is much harder. So QUIC frames are much more complex than TCP frames. And they are built on top of UDP frames, which make the whole thing, the whole analysis much more complex. I'm going to skip this. I'm just going to tell you the results. And see, this is sort of the practice. So using L* and building it into a tool that can be used easily, we managed to learn a full model of TCP, or an almost full model of TCP. And this basically we replicated results of the paper I mentioned earlier in my talk. The key difference with the previous work is that the annotations we had to do to learn this model was about 300 lines of code, whereas their original application of L* required about 3,000 lines of code. And the key difference was that they did not consider the existence of a reference implementation, so they had to implement the whole logic of TCP from scratch. With QUIC, we actually analyzed 4 implementations, 4 large implementations from Cloudflare, Google, Facebook, and then something called QUIC Tracker, which is a reference implementation. And we've learned parts of the protocol, in particular the handshake part. And the model sizes for the handshake varied between 8 and 12 states, and the number of transitions also varied. In order to learn these fragments, we required 10 to 25,000 membership queries. And this is where scaling becomes a problem, and you have to be extremely careful with how you implement these protocols. What is interesting is that even with focusing the analysis on the handshake part of the protocol, we actually discovered 3 bugs in these implementations, and we ended up generating an RFC change. So through the analysis, we discovered that the RFC was too imprecise in one of the descriptions, to the point that the developers would take the description from the RFC and actually introduce a security vulnerability in the implementation. And in light of time, I will not show you the details of the bugs we discovered, and I will just conclude. So I hope I gave you a little glimpse on how one can take classical PL and verification techniques and sort of transport them to network verification. This is definitely very much in line with the previous talk in terms of spirit and how you can do things. And what is really interesting for me in this work is the fact that such a simple algorithm was actually effective in finding bugs and imprecisions in a complex protocol like QUIC. And given that QUIC is still being standardized, this is the right time to actually target it as, as a verification target. And the way we set up the tool is very generic, so it can be applied to network protocols very easily, but also to anything that has to do with state-based models. So if you have a state-based model of a piece of hardware, and you can interact with it, you can also basically make the tool parametric in order to use it in other areas. So that's another thing I wanted to mention. And I'll stop here. Sorry for going a bit over time, and I'll take questions.
Thank you very much, Alex. So there's a couple of questions in the chat. First one, Anka.
Yeah, hi Alexandra, thanks for the talk. I was wondering about the abstraction that you seem to use in the learning algorithm. So how does this work for the equivalence checks?
Right. So, so the equivalence check that we do at the moment is basically we're using exhaustive testing. We're using a bit of fuzzing and testing to implement the equivalence check and to implement the oracle part. And so we use the adapter to basically generate concrete tests to then send to the implementation and to try to get counterexamples. But the only thing we get, a little bit like in bounded model checking, the only guarantee you have is that up to a certain length of trace, what you've seen is or is not equivalent.
Okay, so is it a kind of probabilistic testing or?
Yes.
Okay, thanks.
Okay, Mohammed.
Yeah, so can you explain about the inputs and outputs of the tool? For instance, which language is required for the implementation by the tool? And secondly, for the output, which model checking language is supported currently from the tool that is output?
Right, so that's a good question. So in terms of input, it's not, there's no restriction because—
Hi, Andrew.
Sorry?
Sorry, my... Hello.
Hi, Arti.
Is Mohammed still there?
I'm not sure what just happened, but I'll answer the question and then hopefully if he's not there, he can see the answer later. So in terms of, well, I guess the simple answer is both in terms of input and output, what you can do and what you can connect with is very flexible. So in terms of the connection, in terms of input, as long as your adapter provides the translation, it doesn't matter. Now, in terms of which model checkers we support, at the moment we're outputting the automaton model in a DSL, and then you can use that DSL to translate to whatever model checkers you want. At the moment, we support CBMC and I'm blanking out. I have to look this up, but CBMC at least for sure. But basically, everything is parametric in a way that that you can translate to other languages.
Okay, Michael.
Hi, I just had a question about that output a little bit more detailed. So when you say it finds a bug, what exactly information does it provide to the user, or do they have to analyze that output themselves to see how it differs from what they expected?
Right. So that's a great question. So the way it worked with QUIC, we had traces. So we had concrete examples of packets or sequences of packets that generated outputs that did not seem to conform with what we were seeing in other implementations. And so in the case of the Facebook implementation, we basically took those traces And we had a discussion with the developers on, do you think this output can be explained in some way, or do you agree it is a bug? And it was through the traces, so the fact that the tool can produce concrete packet traces that then the developers can use to go back to their implementation and run the parts that they think might be incorrect or correct. So there was indeed a human loop there in verifying that something was a bug or not.
Okay, so it doesn't identify an issue. It identifies exactly what is happening, and then you analyze that.
Yeah, that's correct.
Okay, interesting.
Okay, there's two more questions. I'm going to take them. We're hearing you very well, Alex, but sometimes your video's not going very well. So if you cut out, we're just going to say thank you now, but I will take these last two questions. So Peter? Peter, are you there? Peter's Zoom has just busted. So Madhusudan?
Yeah, so I was just wondering, just to clarify, because of the answer you gave to Anchor, this is a bug finding tool than a verification tool. Is that true?
That's correct. I wanted to have said that actually we called it the analysis module and not the verification module.
Okay.
Because it is not verification, it's more of an analysis tool. So that's absolutely correct. Thanks, Madhu. I should have said that.
Also, I would imagine that the reference implementation may have made some choices which are not necessary, but it may not exhibit all the behaviors, right? It may exhibit only some because that's enough. So I was just wondering, is there a notion of a non-deterministic or very liberal implementation, reference implementation?
So we do not assume any sort of we do not assume any property about reference implementation. In fact, the reference implementation might even have bugs because it's used to be a comparison tool. So as you are doing your analysis, you might actually find out that your reference implementation was not ideal. And you might replace it with something else. So I suppose, yes, sometimes the reference implementation has non-determinism, and we've seen that in one of the analyses we did. But it's not a problem for the tool because of the analysis part.
Okay, thank you.
Peter, are you there? I think we've lost Peter. So I'm going to say thank you very much.
Our question is on the chat.
Yes, to exercise the target implementation well, don't you need to build a lot of TCP's numerical logic in the adapter?
Yes, so that's what was on those 300 lines of code I mentioned. You need to build that into the annotations you put in the reference implementation.
I think that's all we're going to get from Peter, unless he puts something else in chat. Thank you very much, Alex, and thank you very much for the people doing the giving the questions. I think this has been a super talk, but also a super session this afternoon of much more discussion. It's been great. And I miss everybody in that we're not hearing physically, but I think these last 2 days have been really super. So thanks very much for making it work. I believe it starts again tomorrow at 3:30, Shankar? Is that correct?
I believe so, yeah.
Okay, so it starts again at 3:30 tomorrow. Feel free to be on, to stay on, put your videos on and have a chat now. Otherwise, we'll see you tomorrow, and thank you.
Okay, everyone. Yeah, I'm going to pause the recording, and I can keep the session running for a few more minutes.